Hello student. So today we are going to start welding in our one shot series, right? So let's start welding in a one shot series. So let's see the welding, right? So welding, you can see we are going to join basically two basic material, two parent material are going to be joined, okay, permanently, right? Here this is what, this is the weld pool. As you can see, this is the weld pool, right? This is what, this is the weld pool, right? This is what, this is weld pool, where the liquid metal are going to mix of both the plate, right? So this is the weld pool. We call it, what we call it, we call it bead. This is basically bead, B-E-A-D, bead, right? So this is a base plate, this is a base plate, this is base plate, right? This is also a base plate, this is also a base plate. Now during welding, what happen when you are joining, you are going to transfer the heat. So this portion is called as, 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 this portion is called as heat affected zone. This portion is called as heat affected zone, right? So this is heat affected zone, affected zone. This is what, heat affected zone, right? This is the heat affected zone. Clear? As you go nearer to the weld pool from the base plate, the temperature goes increases, right? The temperature goes increases. When you go from outer surface of the base plate to the near to the heat affected zone, then temperature increases, okay. Then gradually it is increases when you go from the heat affected zone to the boundary of, this is a boundary of what, heat affected zone, right? This is a boundary of what, heat affected zone. Now once you enter into the heat affected zone, then temperature, okay, increases with more rate, okay. Now this is the boundary of heat affected zone and weld pool. And here when you enter into the bead, then where the metal are in the liquid state, then the temperature goes more, increases more rapidly, right? So here the metal is in the liquid state. So this is the basic idea, okay. Now let's move to the next slide. What happened, okay, if you see this weld pool or heat affected zone or your base plate in terms of crystal, my dear, as you can see, this is the grain, initial grain of the base plate. When you are joining, this is the initial grain of the base plate, right? These are the initial grain, okay. This is a base plate. As you can see, this is a base plate, right? This is the base plate and this is a base plate, and you are joining the base plate. This is the, okay, this is a base plate, this is a grain, initial grain of the base plate. This is the initial grain of the base plate. This is the initial grain of the base plate. This is the initial grain of the base plate, right? This is the initial grain of the base plate. Now when you enter into the heat affected zone, this is what, this is the heat affected zone. I'm calling about this, I'm talking about this. See here, in the heat affected zone, the size of the grain are little bit larger than the grain which is present in the base plate. Now the question is, why the size of the grain is larger, okay, in the heat affected zone? This is what, in short, I am calling heat affected zone, right? This is also a heat affected zone. So in a heat affected zone, the grain size is large, right? Grain, because the reason is there will be a grain growth, my dear. There will be what? Grain growth in heat affected zone. Now what do you mean by the grain growth? When you provide the heat beyond the recrystallization temperature, then what happen? The grain are going to be grow, right? The grain are going to be what? Grow. The size of the grain become what? Changes. Now this is the crystal structure in the heat affected zone. Now if you enter into the weld bead, okay, now if you enter into the weld bead, so at the boundary, right, at this boundary, you will get a laminar columbier, you will get a columbier, you will get what? You will get a large regular shaped structure, large regular shaped structure, large regular shaped structure, columbier type structure, okay, columbier type of structure. Then when you go inside, basically it is not a large, it is a elongated columnar structure, right? It is what? It is the, basically this is this, I'm talking about this, okay, long elongated columnar crystal structure. Now if you enter inside this, then this is large grain, okay, large grain. Suppose that after welding, okay, the weld pool is cooled down, so in the weld bead in the center you will get large and regular shape crystal, right? Large and regular shape crystal, but at the boundary you will get long elongated columnar crystal because of sudden cooling. This is what? This is a weld bead. This is what? This is a weld bead, and the weld bead is covered with what? Is covered with oxide. This is the metal oxide or oxide layer, okay. This is the oxide layer which basically protect the, okay, which basically protect the weld pool. So this is the oxide which protect the weld pool, okay. After the welding, that weld pool is going to protected by the oxide. So this is the overall crystal structure in the weld bead. So the question is, what do you mean by welding? The question is, what do you mean by welding? Welding is a process, dear. Welding is a process by which two material, usually metal, are permanently joined, together by coalescence. Coalescence means you are melting the metal and the liquid metal are mixing to each other. That is the meaning of what? Coalescence. Okay, coalescence, that is the meaning of coalescence. Okay, which is included by the combination of how can you mix the metal? How can you mix the metal in liquid state? Either by increasing the temperature, by pressure, and by some metallurgical conditions, right? And some by metallurgical condition. My dear, in welding, high temperature, sometimes high temperature are required, but no pressure. Okay, too high pressure is required with no increase in temperature, right? So condition of welding may be changed, right? Condition of welding may be changed. Sometimes it require a high temperature with no pressure, but sometimes it require a high pressure with no high temperature. In the both condition, metal are going to stick to each other, metal are going to join to each other, right? Metal are going to join to each other. Now let's move to the next point. My dear, welding is what? Welding is positive process. Positive process. Why positive process? Because we are joining two things. Okay, we are adding something. So that's why welding is a positive process, right? Earlier we have seen a machining. Before that we have seen a machining, right? Machining process. Machining is what? Machining is basically a negative process. Machining is basically a negative process because we are removing the thing, right? Because we are removing the thin. Now, in a welding, there are various type of joints, right? There are various type of joints. Like this is a butt joint, as you can see. Okay, this is called as butt joint, right? This is called as what? Butt joint. This is a corner joint. Okay, this is a corner joint, right? And this is the T joint. See, this is the T joint. Okay, this is a lap joint, right? This is a lap joint, and this is a edge joint, because here we are joining edge to edge. So this is known as what? Edge joint, right? Okay, so I think you get the idea of type of joint, right? You get the idea of what type of joint. Now I will discuss about the weldability. I will discuss the idea behind the weldability, right? Weldability is what? The easiness of welding. The weldability of material will depend on the specific welding or joining process being considered. How a material is going to weld in a very easy manner, whose weldability is what? High. But if the material possesses any problem while doing any welding, then its weldability is what? Its weldability is less, right? Its weldability is less, right? So that is the meaning of weldability. In that category, aluminum is very less weldable, right? Aluminum is very less weldable. Then copper is more weldable than aluminum. Cast iron is more weldable than copper, and mild steel is more weldable than, okay, your cast iron. This point is very important, right? This point is very important. Please always remember. I will explain why aluminum. Generally in the exam, either he will ask for from the aluminum, either in the exam he will ask from the aluminum or from the cast iron or mild steel. I will discuss all the three things, don't worry. So this is the weldability. Now what is a fabrication? What is a fabrication process? My dear, fabrication process, basically fabrication weldability test. Fabrication weldability test generally is used to determine mechanical property. Let me listen me carefully. Fabrication weldability test is used to determine mechanical property required for satisfactory performance of welded joint, right? That is a fabrication process. It is a branch which deal to identify whether the obtained joint has a desired mechanical property or not, right? Now for second thing, you have to remember this order, because generally in the exam, examiner will ask this type of things. Now maybe you may ask, sir, why aluminum is least what? Least weldable. Aluminum is least weldable. According to this arrangement, aluminum is least weldable and mild steel is more weldable. Now what is the reason for the aluminum, right? I will write down one by one. Now what is the reason for aluminum? Yeah, what is the reason for aluminum? My dear, for aluminum, actually what happened, the first point I will explain, because the oxide coating on aluminum alloy, generally you find that on aluminum there will be a oxide coating. There will be a oxide coating, right, on aluminum alloy. On aluminum alloy. On aluminum alloy, oxide coating on aluminum alloy. What happened because of the oxide coating on aluminum alloy? My dear, it caused some difficulty in relation to its weldability. Okay, that oxide will resist the heat. That oxide will resist that heat, and the heat is not able to penetrate into the surface of the workpiece, right? So welding is become difficult. Also aluminum has high thermal conductivity. Also aluminum has high thermal conductivity. Also aluminum has high thermal conductivity. High thermal conductivity. Okay, high thermal conductivity. conductivity. Aluminium as high thermal conductivity. Because of high thermal conductivity, what happened? A very short range, a very short temperature range between liquidus and solidus, right? And when the liquidus and solidus means very short range between liquidus and solidus. Suppose this is what? Suppose that this is a liquidus line, right? Above that line, aluminium is in liquid state. This is solidus line. Below that line, aluminium is what? Aluminium is in the solid state. Now, the gap in between liquidus and solidus is small. What does it mean? Means there will be a sudden cooling. Sudden cooling. You know, when the cooling, if the sudden cooling is there, then the grain become what? Brittle of the solid structure. If any structure achieved by sudden cooling, then the grain structure is brittle and the joint become what? In that case, we are basically seeing aluminium, because in aluminium there is a very short range in between liquidus and solidus line. So there is the meaning is that there is a very high cooling rate. It means we are getting a brittle joint in the weld bead. Means the brittle joint, basically we are getting the brittle joint, because in that joint there will be a fine grain, right? So this is a problem. Second case, its viscosity is very low. Okay, viscosity is very low. So to maintain the bead shape, become what? Very difficult, right? That is the main problem. So what are the remedies? Okay, if you want to do a aluminium welding, what are the remedies? We have to take care these 3 points. Along with that, we generally recommend a friction welding or TIG welding, right? We generally recommend friction and TIG welding for aluminium, because friction and TIG is a good method for aluminium joint, right? Also, to remove the oxide layer, okay, we generally recommend AC current. My dear, please listen me carefully. We generally recommend AC current with a high frequency. Because of the AC current, alternating current, what happen? The cleaning of oxide will take place. Right? Removal of the surface oxide from the base metal is obtained with a typical polarity of AC current, right? With a typical polarity of AC current. So this is a problem with the aluminium. So I hope you get the idea of aluminium. Let me discuss with the cast iron. Basically, the problem with the cast iron is high carbon content. High carbon content. Okay, high carbon content. Now, because of the high carbon content and brittleness, because of the high carbon content and brittleness, okay, there is we have to face a very difficulty. What happened during welding? What happened? A massive carbon deposits. Massive carbon deposit have a tendency to form in the area adjacent to the weld. Suppose that we are doing a welding process. This is a weld bead. So massive carbon is going to what? Deposit at the adjacent of the weld bead, and high carbon martensite tends to form, and high carbon martensite my dear, high carbon martensite tend to form in heat affected zone, right? In a heat affected zone, high carbon martensite tends to form in a heat affected zone. In a heat affected zone, this is a heat affected zone. This high carbon martensite is tends to form in a heat affected zone. This microstructure is very brittle. This microstructure is very brittle. When you apply the load, the joint or the heat affected zone is going to be what? With what? Fail. Right? Spontaneously, the crack will be produced. Spontaneously, the crack will be produced when you apply the load. When you apply the load. Right? Okay, am I clear? So what are the remedies? Remedies are generally for cast iron joining. Generally for the cast iron joining, okay, for the cast iron can be joined by the oxyacetylene brazing. This is a remedy. Cast iron can be joined by oxyacetylene, okay, oxyacetylene brazing. Oxyacetylene brazing. By this oxyacetylene brazing, okay, you can join the cast iron or shielded metal arc welding and shielded metal arc welding, right? Shielded metal arc welding. What are the remedies here? We recommend friction welding and TIG welding. TIG welding with AC polarity. Right, with AC polarity. Now, what are the exception in mild steel, right? What are the exception in mild steel or steel? Okay, what are the exception? Okay, what are some minor problem in steel? Basically, what happened, my dear, in the case of stainless steel? You know, stainless steel is difficult metal. Basically, stainless steel compared to this is less problematic material, but stainless steel will show some problem. And why? Because it contains both nickel and chromium. It contains both nickel and chromium, right? Nickel and chromium. It contains both nickel and what? Chromium. Okay, it contains nickel and what? Chromium, right? What happen if it contain nickel and chromium? Basically, it will resist the oxidation, okay, and any reaction, right? And also, when you are going to weld, what happen? That nickel and chromium are going to combine with carbon and precipitate. Precipitate means it will come over the surface, right? It will come over the surface, right? There will be a carbide precipitation. There will be a carbide precipitation. Now, what do you mean by carbide precipitation? My dear, when heat is applied during welding of mild steel or steel, carbon react with chromium. Okay, carbon react with what? Carbon react with chromium to form chromium carbide. Okay, now chromium is coming out, along with carbon is also coming out. So overall strength of the stainless steel or mild steel is going to be what? Decreases, right? That is a main problem. If we deal this thing, then you can easily do the welding of mild steel. So what we recommend? We recommend that we have to use a low arc current setting. With faster travel speed. We have to use low arc current setting, right, my dear? Low arc current setting. Low arc current setting with faster welding speed, with faster welding speed, right? So this is a very important slide, my dear. This is a very important slide. Please remember, a theoretical question may be asked in this session, right? So let's start our welding from the electric arc welding, because a lot of question will be asked from the electric arc welding, right? Because lot of question will be asked from the electric arc welding. Now, what do you mean by the electric arc welding, my dear? In electric arc welding, basically, there is one electrode. Let me show you the another figure if it is possible. Okay, and the figure is not there. Okay. In electric arc welding, basically what happened? The arc is generated between cathode and, okay, let me write down here. The arc is generated here, arc, here, basically arc is generated, okay, arc is generated, my dear, between cathode and anode, between cathode and anode, between cathode and anode. Arc is generated between cathode and anode when they are touched, when they are touched, when they are touched, to stabilize the flow of current, to stabilize the flow of current, they stabilize the flow of current, and then separated by, okay, separated by a small distance, separated by a small distance, right? By this manner you can produce a arc, right? By this manner we can produce the arc. So here, what is the thing? The thing is that there is a electrode, right? There is a electrode, right? And there is a workpiece, right? And here the electrode is what? The electrode is basically, we keep a electrode a negative. It doesn't mean that electrode it doesn't mean that electrode will always negative. It may be that electrode will be a positive. So it is negative, that is cathode, and here we keeping workpiece at anode. Basically we have applied a potential difference in between electrode and workpiece. We touch the electrode and separated by a small distance. Let's say it is a y, right? Let's say it is a y. Then electron will plug out from the electrode, and it ionize the medium which is present in between the electrode and workpiece, and that ions will move toward the respective surface. Like negative ion will move toward the positive surface, and positive ion will move toward the negative surface. Negative ions has a more kinetic energy. That's why at anode 75. That's why at anode almost 70% heat is generated. 70% heat is generated. 70% heat is generated. 70% heat is generated, and the positive ion will move toward the workpiece. Although positive ion have a higher mass, but it has a less velocity, so it has a low kinetic energy. So once they hit toward the negative surface, they will generate only 30% heat. 30% heat is generated. Okay, generated. Am I clear? So this is the case when you apply a direct current. Okay, when you apply a direct current, that is a DC direct current, and when you keep the electrode negative and workpiece positive, then this is a basically straight polarity. So direct current is straight polarity. Straight polarity. Straight polarity. Direct current is straight polarity, right? Direct current is straight polarity. When you apply the when you supply the DC current and keeping the electrode negative and workpiece positive, then this is known as what? Straight polarity. So overall you can say direct current is straight polarity, that is DCSP. That is DCSP, right? That is what? DCSP. Okay, generally state polarity, generally state polarity is recommended. Generally state polarity is recommended, but in some case we recommend reverse polarity. Now, what do you mean by the reverse polarity? My dear, it is very simple. Reverse is reverse of this reverse of state polarity. Now, suppose that there is a electrode. This is an electrode again, and this is a workpiece, right? If the workpiece, my dear, if you keep the workpiece negative and if you keep the tool positive, then this is a reverse polarity, right? Reverse polarity. If you supply the DC current, then you can say direct current, reverse polarity, reverse polarity, right? That is DCRP, direct current reverse polarity. In that case, the thing will be reverse. 70% heat will be produced here, 70% heat will be produced here, and 30% heat will be produced at the work surface. It is clear that whatever be the weld pool is going to be produced in that case has more depth if you compare in the reverse polarity. Okay, if you compare in reverse polarity, okay, if you compare the reverse polarity with the state polarity, the weld pool has low depth, right? The weld pool has low depth. The idea is very simple now. Heat produces at the surface will be low in reverse polarity direct current. So generally the reverse polarity direct current welding is preferred for difficult task. Okay, RPDC, sometime you can say DCRP or RPDC, reverse polarity direct current is reverse polarity direct current, okay, is preferred for difficult task, is preferred for difficult task, such as overhead welding, such as what, my dear? Overhead welding, such as overhead welding, right? Now, either you do a DC current straight polarity, either you do DC current reverse polarity. The Y, that is the arc gap, okay, should be constant. Okay, for a stable arc, for a stable arc, okay, for a stable arc, the gap should be maintained. The gap should be maintained. The gap should be maintained, right? For a stable arc, the gap should be maintained. This is a very important key feature. Okay. Now, the next important thing in the electric arc welding is, okay, this table. Look, this is what? This is state polarity direct current, where the electrode is what? Negative and workpiece is what? Positive, right? Where the workpiece is what? Positive. This is a positive, right? And this is negative. Clear? Now, see here. This is what? This is positive, and this is what? This is negative. This is a straight polarity direct current. Now, if there is any oxide layer on the surface that is not going to clean in this polarity, 70% heat will be generated at this surface and 30% heat will be generated at the tool. Here the weld pool will be deep and narrow. But in case of reverse polarity direct current, where electrode is positive and workpiece is negative, then what happen? The cleaning of oxide layer from the surface is happen. Oxide cleaning action will be take place if the oxide, suppose that if the oxide is present on the surface of the workpiece. Suppose that the oxide is present on the surface of the workpiece. In RPDC welding, whatever be the oxide which is present, right, whatever be the oxide, suppose that a oxide layer is present. Suppose that a oxide layer is present on the initial workpiece. Okay, during welding, what happen? This oxide layer will disappear. Okay, the cleaning action of oxide layer will be happen. But here 30% heat will be generated at the workpiece and 70% heat will be generated at the tool. Dear, if the tool is consumable, then more deposition will take place at the workpiece because tool melting rate of tool is what? High, right? The next thing is that here the heat produces at the surface of the workpiece is less. So the depth of the weld pool is shallow and wide. Okay, weld pool is what? Having a shallow depth and wider, right? But if you talking about AC polarity, in AC polarity what happened? In one cycle, the tool become what? Negative and workpiece become positive. Remaining cycle, the in the next half cycle, the tool become what? Positive and the workpiece will become what? Negative. So cleaning will be cleaning action in which cycle cleaning will happen? In which cycle cleaning will happen? My dear, every half cycle in which the tool become positive and workpiece become negative, in this cycle cleaning action will be take place. And here 50% heat is produces on the tool and workpiece, electrode and workpiece. Here the depth of the weld pool is medium if you compare with the RPDC, little bit larger than RPDC but lesser than SPDC, right? So this is the table. Please remember this table. It is a very important from exam point of view. Now one question may be asked from this point also. Suppose that this is my electrode. As you can see, this is my electrode, right? This is my electrode. Okay, this is the electrode. Now please see this thing. Okay, yes, please see, this is the electrode. When the electrode is going to be melt, then the metal is transferred from the electrode, okay, in this shape. See here, this is the electrode. This is a molten metal which is coming from the electrode, right? Molten metal. Now the droplets are very very thick, so this is known as globular. This is known as what? Globular, right? Globular. Here droplets are coming in the form of a tiny spray, a fine spray. So this mode is known as spray. Basically in the 3 mode, metal is going to transfer from the electrode. Now here continuously the molten metal is coming from the electrode. So it's look like that electrode and workpiece are in contact. okay, through the continuous flowing metal. So it is known as short circuit. Short circuit. Short circuit, right? Short circuit. So please remember this slide also. Okay, please remember this slide also, right? It is a very important slide, my dear. Electrode may be consumable in the welding. Electrode may be consumable and non-consumable. Okay, generally in manual arc welding, is done with the shielded or covered electrode. What do you mean by shielded or covered electrode? Let me explain you. Suppose that if you are doing a manual arc welding, this is the electrode. Okay, this is basically a bare electrode which is made up of metal, and this metal is consumable. This metal is what? Consumable. Now, over this metal, what we will do? We basically we supply some coat. This is a coating. Okay, this is a coating, right? This is a coating. This is a electrode. This is a electrode. This is a electrode. This is a electrode. This is a electrode, right? This is a electrode. 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 This is a electrode, right? But this electrode is a coated electrode, right? This electrode is what? Coated electrode. Coated electrode. Coated electrode. Electrode. This type of coated electrode we prefer in manual. This type of coated electrode we prefer in manual arc welding, right? Manual arc welding. Manual arc welding, right? Manual arc welding. Okay, sometime we are talking about the consumable electrode, right? We are talking about the consumable electrode. I'm talking about consumable electrode. I'm talking about consumable electrode, right? I'm talking about consumable electrode. Sometime we take a uncoated electrode. Okay, uncoated electrode. Sometime we take a uncoated electrode. This is a uncoated electrode, that is a bare wire electrode. Okay, bare electrode, or you can say bare metal wire. Bare metal wire, right? This bare metal wire generally prefer in automatic welding. Automatic welding, right? Automatic welding. This type of bare wire electrode will be prefer in automatic welding. Yeah. Now I will tell you one thing. Okay, we will discuss this later. We will discuss that thing later. So this is a thing, my dear. Okay, this is a thing. So please see a question. In the question was asked in GATE 1993. The question was asked in GATE 1993 in DC welding. The straight polarity electrode negative result in lower penetration. No, penetration is high. Lower deposition rate, lesser heating of workpiece. No. A smaller weld pool. No. Lower deposition rate. Why? Because at the electrode, suppose that this electrode is consumable. Suppose that it is a consumable electrode. Consumable electrode. Electrode is going to be what? Consume. Electrode. Suppose that it is a consumable electrode, and here workpiece is there. Suppose that here it is a straight polarity, that is negative, and that is what? Positive. So 70% heat is produced at the plate and 30% heat will be produced at the electrode. So less heat is available at the electrode, so less consumption of the electrode will be there in per unit time. If the electrode is going to be melt, then the deposition will take place on the base plate. So less deposition will take place. Lower deposition rate will be happen. right? Lower deposition rate will be happen. Now let's discuss the arc welding equipment. My dear, in arc welding equipment, there will be two types of welding, right? There will be two types of equipment generally we prefer. First is your drooper, in which constant current welding machine is used. In which constant current welding machine is used, and generally these type of machine is generally used in manual arc welding. Okay, manual arc welding. What do you mean by a constant current welding machine? Constant current welding machine, that is I of arc equal to I of transformer. I of arc equal to I of transformer. Whatever current is coming from transformer, it is what? It is equal to I of arc, right? It is preferable for manual arc welding. Now the second is constant voltage machine. Here the voltage is remain constant, okay, and generally it is good for manual arc welding, right? It is good for what? Manual arc welding. So always remember, it is good for manual arc welding. Here whatever be the arc voltage equal to transformer voltage, whatever be the arc voltage equal to transformer voltage. My dear, let me give you some point regarding to the constant current characteristic. Dear, in a constant power source are used primarily with a coated electrode. So generally we use here a coated electrode. Already we are doing manual welding, and manual welding, you know, we generally prefer a coated electrode. This type of power source has a relatively small change in what? A small change in amperage. A small change in amperage, and arc power for a corresponding relatively what? Large change in arc voltage or arc length. Thus the name constant current. Suppose that the arc length is going to be changed, right? But the current is not going to be what? Change in a very high manner. See this figure? This is a figure of drooper. Okay, this is a voltage versus what? Voltage versus I. Suppose that for any reason the voltage is going to be changed. Suppose that for any reason the voltage is going to be changed, whether you supply more voltage or less voltage, whether the R gap is going to increase or reduces, then what happens? The voltage is going to be changed. Okay, suppose that at V1 voltage, this is the I1 current, right? And at very large change in voltage, that is V2. See, this is what? This is I2. My dear, please see, the change in current is what? Very small, almost negligible change. The characteristic of this power source, the characteristic of this power source are best illustrated by observing a graph. That plots the volt amperage curve as can be seen in this figure. You can see in this figure. My dear, please see this figure. This figure is very important. Seen in this figure, the curve of constant current machine drops down. The curve of constant current machine drops downward rather sharply. And for this reason, this type of machine is often called a drooper, right? So I hope my point is crystal clear regarding this graph. Let me discuss a constant voltage characteristic. In the constant voltage characteristic, you have seen that V of arc equal to V of transfer. Okay, my dear, in this welding, you can see the relation between power source, that is voltage, and amperage, that is current. There will be a straight line which is a steeper, right? There is a straight line which is steeper. Now please let me explain you this graph. My dear, constant voltage power source, also known as constant potential, are used in welding with solid and flux coated electrode. And the name implies the voltage output remain relatively constant, means whether you do a whether you use a coated electrode, whether you use a coated electrode or uncoated electrode, it doesn't matter, but the voltage remain constant. But the voltage remain constant. The voltage output, whatever be the output voltage, that is a arc voltage, remain constant. Second point, on this type of power source, the voltage on this type of power source, the voltage is set. The voltage is set at the machine, and amperages is determined by the speed. Amperages is determined by the speed that the wire is feed to the welding gun. Okay, I mean current you are going to set according to the feed of the wire, according to the feed of the wire, right? Suppose that if you want less consumption, then current is changed, that current is less. If you want a more consumption of wire, means more melting of wire, then current have to be increased, right? Increasing the wire feed speed, increasing the wire feed speed, you have to increase the amperage. Decreasing the wire feed speed, decreasing the wire feed speed, you have to decrease the amperage, but output voltage remain constant. Am I clear? So this is the voltage current characteristic, and here the graph is linear, right? Whatever be the reason, if the voltage is going to be changed, my dear, if you change a little bit voltage, then there will be a large change in current. Then there will be a large change in what? Large change in current, right? So if the line is going to touch here, it is called as open circuit voltage. If this line is going to touch at the current axis, this is known as short circuit current with no voltage. Short circuit current basically with no voltage. So you can write down the intercept form, that is V divided by open circuit voltage plus I divided by short circuit current equal to 1. Right? So this is the equation we generally use in linear characteristic, in linear power source characteristic, right? So what do you mean by OCV? OCV is a open circuit voltage. Basically OCV, my dear, OCV is the maximum rated voltage. OCV is the maximum rated voltage between open terminal under no loading condition, And what do you mean by short circuit current? Short circuit current, it is the maximum rated current. It is the maximum rated current that is required during arc generation. I hope my point is crystal clear. Let's move to the next point. Okay, let's move to the next point. Now, sometime what happened now? See, this is figure, what I'm telling. This straight line, the steeper line is going to touch here and here at the voltage and current. And this is a linear relation. Okay, this is a linear relation. Sometime in the welding, suppose that you are using a electrode whose diameter is what? Let's say whose diameter is, this is the diameter of the electrode. This is what diameter of the electrode. So what should be the optimum? What should be the, my dear, what should be the, I think it is not clear now. It is not clear. See, this is, I'm talking about this, right? I'm talking about this, right? I hope it is clear. Now, what should be the optimum? Suppose that this is the diameter of the electrode. What should be the optimum gap in between electrode and workpiece? The optimum gap, theoretically, the optimum gap should be equal to the diameter of what? Should be equal to the diameter of the electrode. So arc length should be equal to, for optimum condition, I'm talking about for optimum condition, right? I'm talking about for optimum condition. So in optimum condition, arc length should be equal to arc length should be equal to arc length should be equal to the diameter of the electrode size, should be equal to the diameter of electrode size, right? Now, what should be the optimum width of the pool? Right, what should be the optimum width of the pool so the weld quality is good? Okay, the bead width, this is the width, right? This is what? This is the width. This is the width of the bead, right? The width of the bead. So here the bead width should be equal to bead width should be equal to, okay, should be equal to 3 diameter of the equal to 3 diameter of the electrode right, of the electrode. So I think this point is crystal clear. Okay, I think this point is crystal clear. Now let's move to a question. A very good question is there. Let's see this question. Okay, let's see this question. Before that, let's solve this question, right? The DC power source for arc welding has the characteristic 3V plus I equal to 240. My dear, it is a linear characteristic now. So it is what? Constant current characteristic, constant voltage characteristic, where V is the voltage and I is the current. For maximum arc power at the electrode, voltage should be set. For the maximum arc power, what should be the arc voltage, right? You have to find out. Okay, now I will give you one trick, right? One trick for maximum arc power. For maximum arc power, what should we have to do, right? What should we have to do for maximum arc power? We know that V divided by open circuit voltage plus I divided by short circuit current equal to what? 1. Arc power equal to V of arc, okay, into V of arc into what? I of arc, right? I of arc. Am I clear? Actually, my whole analysis will depend on this, right? Now, you know that for constant current, voltage, for constant voltage, V of arc equal to V of transformer. Okay, so from here what you can write? You can write 1 minus I divided by short circuit current into open circuit voltage, right? Put here P of arc, right? That is equal to 1 minus I by short circuit current. Here I, basically you are putting here what? Transformer voltage. So you will be get what? I of arc, right? So here I of arc. Now my dear, for maxima minima, differentiate that arc power. Differentiate with respect to what? I of arc. Now here I of arc, that is what? 1 minus twice I of arc divided by what? Short circuit current. Okay, divided by what? Short circuit current, equal to what? 0, right? Equal to what? 0, equal to what? 0, okay? Equal to what? 0. Now, this is equal to what? This is equal to 0 now. So, it comes that I of arc equal to short circuit current divided by 2. For maximum arc power, I of arc is what? Half of short circuit current. If you put the value I of arc here, then you will get V of arc, OCV, plus I of arc is short circuit current divided by 2, right? Divided by short circuit current equal to 1. So, V of arc will become, okay, V of arc will become 1 by 2 OCV. OCV divided by 2. So, always for maximum arc power, you have to reduce, you have to take half of the OCV for arc voltage, and for arc current, take it half of the short circuit current. So, directly now onwards, don't do any calculation. First of all, convert it into intercept form. So, it is what? 3V plus I equal to 240. So, V divided by 240 divided by 3 plus I divided by 240 equal to 1, right? So, V divided by 80 plus I divided by what? 240, right? Now, 80 is what? Short circuit current. So, for maximum arc power, what should be the voltage? The voltage V of arc should be what? 40 volt, right? 40 volt, half of the short circuit current. If the examiner suppose that if he asks what should be the current, then half of the 240, that is 120 ampere, right? 120 ampere. This is the answer for maximum arc power, right? This is the answer for maximum arc power. I hope the point is crystal clear, right? I hope the point is crystal clear. Now, let's move to the next question, my dear. Let's move to the next question, right? Before moving to the next question, before moving to this question, I have to tell you one thing, okay? I have to tell you one thing. And what is a thing? What is a thing? What is a thing? What is a thing? Just a minute. Just a minute. Okay. Yes. You can see. Or I will explain it on the next slide. Please see. Suppose that whether you are doing any welding, right? This is the electrode and this is the workpiece, right? And this is what? This is the arc length, that is L. So, what will be the arc voltage? Basically, arc voltage will depend on the arc length, right? So, the arc voltage is A plus BL. A and B are what? Constant, and L is the length in mm. So, this will give you what? Volt. L is a length in mm, arc length in mm, right? Arc length in mm, and it will give you what? It will give you the arc, it will give you the arc voltage, right? So, please remember this thing. A and B are what? Constant, and L is the arc length. L is the arc length whose value L will be in what? In mm. Okay, A and B are constant, right? A and B are constant, L will be in mm. So, please remember this point. Okay, please remember this point. Now, let's move to the question. Okay, let's move to the question, my dear. Let's move to the question. In a DC arc welding operation, the voltage arc length characteristic was obtained. That is, V of arc is given to you. Okay, that is, V of arc is given to you. That is 20 plus 5L, right? Where the arc length L was varied 5 mm to 7 mm, right? Here we are denote the arc voltage in volts. The arc current was varied from 400 ampere to 500 ampere, assuming linear power source, characteristic. The open circuit voltage and short circuit current would be, you have to found, right? You have to found. Now, my dear, here the arc voltage is given, right? Here, this is the solution. This is the solution. Here, V of arc is given. That is what? 20 plus, let me see, 20 plus 5L. 20 plus 5L, right? 20 plus 5L. Now, what will be the V of arc when L equal to 5 mm? It will be 20 plus 5 into 5, that will be 45 volt. What will be V of arc when L equal to 7 mm? That is 20 plus 5 into 7, 55 volt, right? Now here constant voltage characteristic is there. Constant voltage characteristic is there, right? So here you can write the V and here you can write the I. Dear, please see what is given. Here V of arc denote the arc voltage in volt. The arc current was varied from 400 to 500. According to the length, the current is also going to be changed, right? 400 to 500. Now, what is the arc voltage? Arc voltage are here 45 and 55. Let's say this is a line, right? This is a line and this is open circuit voltage and this is short circuit current. Open circuit voltage and this is short circuit current we have to find. Now, my dear, corresponding to 45 volt, there will be a current, yes or no? Corresponding to 55, according to this graph, there will be a current. Now, corresponding to 55, this current is obtained. Corresponding to 45, this current will obtain, and here the current ranging from 400 to, here the current ranging is 400 to 500. So, 400 will be comes here. You can see, according to the 55 volt, the current is less. So, 400 to, let me see the value, 400 to 500, right? 400 to 500. Now, you got the 2 points of this line, 2 points, okay, 2 points. So, can you find the equation of line? Yes, we can find the equation of line, right? So, this point will be point 1, that is 400, 55. This is point 1 and this is what? 500, 55. This is point 2, right? This is point 2. So. See, now we have to apply the equation, that is y minus y1 divided by x minus x1, y2 minus y1 divided by x2 minus x1, right? Now here y, that is what? V minus y1, that is 55, divided by x, that is I, minus x1, that is minus 400, okay. Now y2, that is 55, sorry, it is a 45, it is what? 45, yes. So y2, that is what? 45. 45 minus 55, divide by 500. 500 minus 400. So V minus 55, I minus 400, minus 10 divided by minus 10, 500, that is what? Minus, plus 100, right? Plus 100. Am I clear? So 45, 45 minus 55, right? 500 minus 40. Now this 0 cancel. V minus 55 into 10 and into 10 and minus I minus 400. V10 minus 550 minus I plus 400. 10 V plus I 950. V divide by 95 plus I divide by 950 equal to 1. Dear, you get the equation, right? You know that V divide by open circuit voltage plus I divide by short circuit current equal to 1. So open circuit voltage is 95 volt. 95 volt and short circuit current is what? 950 volt. Oh, sorry, ampere. This is what? Ampere, right? This is ampere. So I hope you understand the concept. Okay. Now let's discuss a heat input, right? So I'm going to discuss a heat input concept. Heat input. Heat input, right? So what do you mean by heat input here? Suppose that we are doing a welding operation. This is my workpiece. This is my, here you can see that this is my workpiece, right? This is the workpiece and this is the length . So this is the workpiece. Suppose that we are doing a welding operation, right? We are doing here a welding operation. This is my welding operation. This is my welding operation, right? Okay. Yes. See here. We are doing here a welding operation. This is a weld pool, as you can see, right? Now there will be a electrode, right? There will be a electrode. This is the electrode, right? And there will be a V of arc, right? Arc voltage and arc current. So the power or heat which we are giving, okay, to the weld pool is what? The arc power which we are giving is what? That is V of arc into I of arc, right? Into I of arc, right? Now here the electrode is moving with some welding velocity V. V is the welding velocity, right? V is the transverse or welding velocity along weld pool, along weld pool, right? So let's say the arc, okay, so it will be what, that is joule per second. Okay, the power will be in watt, that is joule per second, and let's say the welding velocity will be in mm per second. Okay, so the heat input, in short I will say it is HI. So the heat input, my dear, it will be arc power divided by welding speed, right? And it will become joule per mm, right? Joule per mm. So per unit length, that much energy, that much heat in terms of joule is going to be what, distributed, right? So that is the heat input. Okay, the basic idea of the heat input. So let's solve one question in the heat input so that you will get a better idea. Okay, a better idea in the heat input. The question generally asked in GATE 2015, right? It was asked in GATE 2015. And what was the question, my dear? Let me write down the question, not a completely. I'm going to write down the data. The language of the question is that during TIG welding, during a TIG welding process, the arc current and arc voltage were 50 ampere and 60 volt. Okay, the arc, there will be a case. Let's say this is a case 1. Here arc current and arc voltage is given. So arc voltage is what and arc current is what? Arc current is 50 ampere and arc voltage is 60 volt, right? 60 volt. Now you are doing you are using that much arc current and arc voltage, and the electrode is moving along the weld pool with a speed of 150 mm per minute, right? With the welding velocity 150 mm per minute, right? Mm per minute. Now my dear student, here in another process, the TIG welding, okay, in another process the same TIG welding is carried out at a welding speed of what, 120 mm per minute. Now the welding speed is 120 mm per minute, right? The welding speed in case 2, this is a case 2, similar arc welding of TIG, okay. Mm per minute, the same arc voltage. So here the arc voltage is same, that is 60 volt, that is 60 volt. You have to find the arc current for what, for same heat input. In both the case 1 and case 2, okay, heat input is same, heat input is same, heat input is same in case 1, in case 1 and 2, right? In case 1 and 2, heat input is what, heat input is same. So you have to find the desired current. You know what is the heat input? Heat input either for case 1 or case 2, what you will write, arc power, that is 60 into 50 divided by what, divided by 150, right? Also the heat input is same, so you can write I, okay, I into V, that is 60 divided by 120, right? 120, right? Same arc voltage is there. Now you have to divide it by the, okay, speed. Now 60 is same, 60 is same. Now here I will becomes 120 into 50 divided by 150, right? 0 0 5 3s and 3 4s, it comes out 40 ampere. It comes out 40 ampere. So I will be what, I will be 40 ampere, right? 40 ampere. I will be 40 ampere, 40 ampere, right? Now, I hope you understand the concept, right? I hope you understand the concept. Now, let's move to the another question, my dear student. Low carbon steel plate is to be welded by a manual metal arc welding process using a linear VI characteristic. Using a linear VI characteristic is what? That voltage is constant. If voltage is constant, then V divide by open circuit voltage plus I divide by short circuit current equal to 1, right? DC power source, the following data are available. Open circuit voltage is given, that is 62. Short circuit current is given, that is 130. Arc length is given, that is 4 mm. Transverse speed of welding, that is 15 centimeter per second. Efficiency of heat input is 85%. Voltage is given, right? Voltage is given as calculate the heat input into the workpiece. Okay. So, my dear, what we do here? Okay. So V of arc, basically we have to find V of arc, right? We have to find V of arc. Okay. So for L equal to, okay, let's start with the question. Let's start with the question here. You can solve the question here, right? You can solve the question here. Now, I can write that, I can also write here, V divided by 62 plus I divided by 130. Efficiency of heat input is 85%, right? Okay. So you have to find out the power, right? You have to find out the power. So just let me do this question. Okay. Now, you have a arc length. Arc length means you have this is the electrode and this is what? This is the workpiece. So this is what arc length and that arc length is 4 mm. So here the arc voltage, V of arc voltage will be what? 20 plus 1.5 into 4, right? So what will be the arc voltage? 1.5 into 4 plus 20, that is 26 volt, right? 26 volt. Now you know the V of arc, right? And for a VI characteristic, we can know the we know that V of arc equal to V of transformer, right? V of transformer. So here you can put V of arc, that is 26 divided by 62 plus you will get the corresponding I of arc divided by 130 equal to 1. So I of arc will be 1 minus answer divided by 62, answer into 130, so 75. So which implies that here I of arc will be 75.48 ampere, right? So arc power will be V of arc, right, and I of arc. Now it will be what? It will be V of arc is what? 26 multiply 75.48, that much what will come. So answer into 26, it will come 1962.58. It will come 1962.58 watt, right? Now the efficiency, this is basically a input P of arc. This is input, right? This is input, but actually how much is receiving here? But actual how much this zone is going to receive. So basically P of actual is 0.85 into 196.2.58, right? So answer into 0.85, it will be 166, it will be 166.8.1935 watt. Now my dear, here actually he wants heat input into the workpiece. So we know that heat input equal to 166.8.193, okay, divide by welding speed, that much watt means that much joule per second, right? That much joule per second, and welding speed, transfer speed is 15 centimeter per second, 15 centimeter per second. So second cancel, joule per centimeter. So answer divided by 15, it will comes out 111.21 joule per centimeter, right? So this will be the, okay, this will be the final answer. So I hope these two questions are crystal clear to you people. Now let's move to the next portion, right? That is what? That is the duty cycle. That is what? That is the duty cycle. So what do you mean by the duty cycle? A duty cycle basically, the red one is not clear to you. Duty cycle is a basically welding equipment, okay, duty cycle is a welding equipment specification, right? Welding equipment specification, which defines the number of minutes within a 10 minute period during which a given welder can safely produces a particular welding current. Out of 10 minutes, how much time you will take to do a safely welding? Suppose out of 10 you will take 7 minutes, okay, for welding safely, and rest of the minute you will take rest. Not you, basically the instrument during 7 minutes, what happened during welding? The instrument gets heat up. So after 7 minutes you give a 3 minute, okay, so that it will cool down, right? Then after you will start the welding. So let's try to understand this concept with the help of example. Like 150 ampere, okay, a welder is taking 150 ampere current, a welder is taking with a duty cycle of what? 30%. Okay, with a duty cycle of what? 30%. So what is the meaning? Basically 150 ampere, okay, current is taking a welder with a duty cycle 30%. So let me explain this concept. Suppose that this is a welding equipment, right? This is a welding equipment, and you are withdrawing how much? You are withdrawing 150, you are withdrawing 150, right? 150 ampere current from this transformer, okay, from this transformer at the rate of what? 30% duty cycle, right? So what is the meaning? That 30% duty cycle means out of 10 minutes how much you are taking? You are taking a time, okay, safely welding. So 30%, 0.3 into 10 minute, it will give you how much? 3 minutes. So this is a safely welding time. This is a safely welding time, right? Rest 7 minutes out of 10, rest 7 minutes, welding is stop. Welding is stop. Why welding is stop? Because the instrument gets heat up. So during 7 minutes it will cool down. Once the 7 minute will over, then again we are going to start welding. Means from the 11th minute we are going to start welding from 11 to 13. We will do a safe welding, and from 14 to again, okay, then again after 13 minute, after 13 minute, we will take a rest up to 20 minute, right? So this is the thing. Okay, so this is a thing. This is the what welding. In welding, this is a concept of duty cycle. Now, this is a fact that if you are doing a manual welding, my dear, this is a fact. You should be note down that. If you are doing a manual welding, then in manual welding, generally we keep a 60% duty cycle. What do you mean? In 60%, on an average, the duty cycle is 60%, means out of 10 minutes, 6 out of 10 minutes, generally we take a 6 minute for a welding, okay, on an optimal value of the current, right? And for a automatic welding, duty cycle is what? 100%. What is the meaning that duty cycle is 100% for automatic welding? My dear, in a automatic welding, suppose that this is a transformer, okay, suppose that this is a transformer, right? Suppose that we are doing a automatic welding. This is what? Automatic welding, right? Automatic welding. Here automatic welding is what? 100% duty cycle, means out of 10 you can do a continuous 10-minute welding, right? Basically, in the case of automatic welding, what happened? There is a system, okay, which cool downs. There is a system, okay, there is a system which takes the heat from the transformer. This is your transformer, right? This is your transformer, okay, transformer, and this is some cooling system. Like this is some what? Cooling system which continuously takes heat, takes heat from transformer, right? So there is no need to stop a welding in the case of automatic, right? So this is the thing that in automatic there is a 100% duty cycle, but in manual welding, generally we keep 60% welding cycle. It is not fixed. 60% is not fixed. It can be vary like that. Okay, it can be vary. Okay, it can be vary. So the thing is that this is a standard specification. Suppose that if I change the current, if I change that, now I want 200 ampere, then what should be the duty cycle, right? What should be the duty cycle? If I'm withdrawing 200 ampere current from the transformer, then what will be the next duty cycle? I want to know, right? I want to know. This is the very important thing, my dear. This is a very important thing, because this is a rated. This is what? Rated thing. Okay, this is the rated. The current is rated, the duty cycle is rated. It is already mentioned on the transformer. But now suppose during welding you need a 200 ampere, right? Then how can you find the duty cycle corresponding to 200 ampere? So there is a formula. Let me write down. There is a formula. This is what, my dear? Rated current. So IR. This is what? This is rated duty cycle. So IT. This is basically T. T stand for duty cycle. Okay, TR. That is the rated duty cycle. So my dear, you have to write down IR square into, that is rated current square. Okay, rated current square, rated duty cycle equal to, okay, you are withdrawing that actual, current. So actual current which you are withdrawing, this is the actual duty cycle which you want. Then how can you find? You can find that actual duty cycle will be what? IR by IA whole square into TR. This is your required duty cycle corresponding to that current. This is the required, this is the required duty cycle. This is the required duty cycle. I hope you understood this concept, right? I hope you understood this concept. Okay, so this is a thing. Okay, or suppose that I will take one example, one numerical example, so that you can understand this thing. Already the thing is mentioned here, and for your better understanding I will take one numerical example. Let's say there is a question. I will take a question. 200 ampere power source, 200 ampere power source, okay, 200 ampere power source rated at 60%, rated at 60% duty cycle, 60% duty cycle, 60% duty, okay, cycle, 60% duty cycle, and operated at how much? 250 ampere, 250 ampere, right? Operated at what? 250 ampere as per permitted, right? As per permitted, as per permitted, as per permitted. Now, so we have to find the corresponding duty cycle, okay, which corresponding duty cycle according to 250 ampere. So this is the rated current and rated duty cycle. So rated current square, rated current square, rated duty cycle, rated duty cycle, actual current square, okay, actual duty cycle. So rated is what? 200, rated duty cycle is 0.6, okay, and 250 square, now you can find TA. Now you can find the value of what? TA. So what will be the value of 200 divided by 250? Answer square, answer into 0.6. It is coming 0.384. In terms of percentage, 38.4 percentage. Okay, in terms of minute, this is in terms of fraction, this is in terms of percentage. This, if you write in terms of minute, then answer into 10 means 3.84 minute, right? 3.84 minute. Out of 10 minute, okay, 3.8% out of 10, at 3.84 minute, you can do continuously welding by using 250 ampere. Here you can see clearly that if you increase the current, then duty cycle decreases from 60% to 38.4%. It clears us that by increasing the current, the dissipation of heat is also increases. The dissipation of heat also increases, my dear. So always when you increase the current, so it is clear, okay, it is very clear, the concept is very clear. What is the concept? That if you increase the duty cycle, right, if you increase the current, if current is increases, which implies duty cycle decreases, or vice versa. If not vice versa, if current is decreases, it is increasing. Now if you decrease the current, decreases, which implies that duty cycle increases. So please remember this concept, right? Please remember this concept. Okay, now let's move to the next slide and let's solve a question. Okay, a very good question is there. Please see this question, what it tells, right? What it tells, please see. The arc length voltage characteristic of DC arc is given by V equal to 24 plus 4L, right? V equal to 24 plus 4L. Here arc voltage 24 plus 4L, where V is a voltage in volt and L is the arc length in mm. The static volt ampere characteristic of the power source is approximately by a straight line. Power source is a straight line. So V divided by open circuit voltage, transformer voltage divided by open circuit voltage, transformer current divided by short circuit current equal to what? 1. Okay, with a no load, that is open circuit voltage is given and short circuit current is given, that is 600 ampere. So you have to determine the optimum arc length for maximum power. What will be the optimum arc length for maximum power? My dear, you can solve this question by two ways, either by a conventional way and by a short trick. Generally, I recommend a conventional way. Why? Because if you first of all try to understand the conventional method, later I will tell you the short trick, right? Within a second you can find the answer of this question, but you need to know the conventional method, right? You need to know the conventional method of this question. So what should be our approach here, right? What should be our approach here? Now let's try this question. Okay, let's try this question. Okay, now here you can see that in this question, okay, so see here, dear friend, see here it is given that V divided by open circuit voltage, that is 80, plus I divided by short circuit current, okay, I divided by short circuit current equal to 1, right? Now V of arc is given. So for a maximum power, for a maximum arc power, so P of arc equal to what? P of arc is V of arc into I of arc, right? V of arc is given to us, that is what? That is 24 plus 4L. That is 24 plus 4L. 24 plus 4L, right? Volt. This is volt. L is in mm. Now we don't know the I of arc. My dear, suppose we know that there is a straight line characteristic. So in a straight line characteristic, V of arc equal to what? V of transformer. So put here that 24 plus 4L divided by 80, okay, plus I of arc, short circuit current, sorry, here short circuit current is what? Here the short circuit current is 600, right? Here the short circuit current is 600. So short circuit current is 600, right? So here I am going to write 600, okay, 600. Now I of arc divided by 600 equal to 1. Now what will be the I of arc here? 1 minus 24 plus 4L. This is a conventional approach. I will tell you the simple approach also, right? So what can you write? You can write here 80 minus 24. I of arc divided by what? 600. I of arc divided by 600. So minus 24 minus 4L divided by what? Divided by 80, right? So see here, I am going to solve this question, right? So I of arc divided by 600 equal to 80 minus, so it will come 56 minus 4L divided by what? 80. Now I of arc equal to 56 minus 4L, okay, so 600 divided by what? 80, right? 0 0, and here this I of arc equal to 56 minus 4L. So it comes out 60 by 8. So 2 4s and 2 4s and 2 3s, and again then 2 2s, 2 1s, and 10 15. So 15 by 2, right? 15 by 2, or you will keep it as it is if you want. Now P of arc equal to what? V of arc multiply I of arc. Now my dear, you have a V of arc and I of arc. So put here. So it will be 24 plus 4L, and it is 56 minus 4L, 15 by 2. Now for maxima minima, this is what P of arc, right? This is what P of arc. For maxima minima, differentiate P of arc with respect to L and put equal to 0. You will get L equal to what? 4 mm. You will get L equal to what? 4 mm, right? I think so. I think so, right? I'm saving here your time. If I do the differentiation, okay, it will become 4 mm. Please check by yourself, right? But I will check this answer by a short trick. You know that for maximum arc power, what is V? What is V basically? Half of OCV, right? What is V? Half of OCV. So OCV is what? 80 divided by 2. And what is arc voltage? What is arc voltage? That is what? 24 plus 4L, right? 24 plus 4L, 80, that is a 40. 40 minus 24, answer divide by 4. So here, my dear, L comes 4 mm. So see, here we are getting same thing. Okay, within a 2 step, you get your answer. But here the process is lengthy. But to understand this, you should know the conventional approach, right? You should know the conventional approach. Then go for a short trick. Then go for what? Go for a short trick, right? So I hope you understand this thing. So let's move to the another concept, that is okay. Now let's move to the another concept. And before arc blow, I want to discuss regarding the electrode, right? I want to discuss regarding the electrode. My dear, what do you mean by the electrode? You know the electrode by which you are doing the welding. Electrode are of two type, that is non-consumable electrode, non-consumable electrode, and second is your consumable electrode. Right? Consumable electrode. My dear, in non-consumable electrode, generally we prefer carbon, graphite or tungsten. Right? In non-consumable electrode, generally we prefer what? We prefer a carbon electrode, right? Carbon, graphite or tungsten, right? Or tungsten. We prefer tungsten, right? We prefer here tungsten. In consumable electrode, it depends on the type of base plate or base metal, because the bead combination should be same. Okay, should be same according to the base plate. So if in non-consumable electrode, the electrode is not going to be consumed. So what is the advantage? Arc length remains same. Arc length remain same, right? Remains same. If arc length remains same, arc is stable. Okay, arc is stable without any defect. I mean, the defects will produce less in this case. Okay, the defects will be produced. Okay, will be less. Now Consumable electrode. My dear, here if you talk about the consumable electrode, so in consumable electrode, basically it provide the filler metal. Okay. Second, it provide the filler metal. Second, same composition as the material to be welded, right? Same composition, right? Same composition as the material to be welded, as the material to be welded, same composition as the material to be welded, right? But here you have to move the electrode toward the workpiece to maintain the gap. Okay, this required that the electrode to be moved toward or away from the workpiece to maintain the what? To maintain the arc. Okay, and satisfactory welding condition. We have to move the electrode to maintain arc length, right? To maintain arc length, you have to move the electrode to maintain the arc length. So this is the required thing, right? So this is the required thing. Consumable electrode are of basically three kinds. Also, if you go into the detail, then consumable electrode are of three kinds. First, a bare wire. Second is flux coated, and the third one is a coated or extruded, that is highly shielded electrode. Right? In case of automatic welding, please remember one thing. Okay, please remember one thing. In case of automatic welding, we generally prefer bare electrode. Right? We generally prefer what? Bare electrode, right? In the form of wire. Bare electrode in the form of wire. Right? In the form of continuous wire, or I will write in the form of continuous wire. In the form of continuous wire or coil, right? In the form of continuous wire or coil. Okay. So I think this is more than enough to the electrode. Okay. Now let's move to the arc blow, right? Let's move to the arc blow. Here you can see the figure, my dear. If you are not able to see, then I am going to redraw it. Okay, I am going to redraw it so that you can understand. My dear, this is the electrode basically. This is what? This is the electrode. See here, this is the electrode. See here, this is the electrode, right? This is the electrode. Okay, electrode, you know, it is a conductor. Electrode means what? A metal that is what? Conductor, right? Conductor. Now, in electrode, current is flowing, right? In electrode, current is what? Flowing. If the current is flowing, okay, if the current is flowing, whether from in this direction or in this direction, depending upon the polarity, right? Depending upon the polarity. So I'm not drawing here. I'm just drawing a simple line. This represent the current. Depending on the polarity, the sign of the direction of the current is going to be what? Change. Now, a flowing current will do one thing. Remember what? It will produce its own magnetic field. It will produce own magnetic field. It will produce its own magnetic field. It will produce its own magnetic field. Right. So this is a magnetic field which is produced by the current carrying electrode. Now what happened, my dear? Below that electrode, there will be what? There will be a arc. There will be arc. Okay. Arc is what? Basically, here ions are there, right? Here basically ions are there. and these ions basically are charged particle, that is plus and negative, and these charged particle or ions will deviate because of the magnetic field line. They deviate. The arc is not concentrated toward the workpiece. The arc will deviate whether in this direction, whether is this direction, depend on the net magnetic field. Suppose that because of the magnetic field line, the net magnetic field in this direction, right, the net magnetic field is in this direction, then arc will deviate in this direction. Suppose that the net magnetic field, suppose that the net magnetic field is in this direction, then the arc is going to deviate in this direction. It depends on the net magnetic field. Suppose that the magnetic field is flowing in this way, so magnetic field will be deviate in this direction. Suppose that magnetic field is in this direction, so net magnetic field in this direction. Not only the magnetic field of the current carrying wire, the overall thing is that unbalanced magnetic field. Unbalanced magnetic field will be produced if the base metal is a conductive material. If the base plate is a conductive material, if the base plate is a magnetic, if the base plate is what? If the magnetic, then if the base plate show a magnetic property, then also the arc flow will be occur, right? The arc flow will be occur. So I hope you understand little bit, you visualize now, you are able to visualize what do you mean by a arc flow. So this is what, my dear, this is arc flow. This is what? This is arc flow. This is arc flow, right? This is arc flow. Now try to understand this thing. Okay, now I'm going to elaborate. I'm going to write each and every point regarding to the arc flow. Generally, arc flow is what? Generally, my dear student, yes, so arc flow occur. Okay, arc flow occur during the welding of what? Magnetic material. Arc flow occur. Arc flow occurs. Why? Some of the basic point. During welding of magnetic material, during welding of magnetic material, during welding of magnetic material. Second, right, the effect of arc flow. The effect of arc flow is maximum when welding corners with a magnetic field, because magnetic field is concentrated at the corner. Also, when welding with a bare electrode. When welding with a bare electrode, if you are welding with a bare electrode, then also arc flow will be occur. Overall, there will be unbalanced magnetic field. Unbalanced magnetic field. Okay, unbalanced magnetic field can be act due to the current carrying wire or due to the magnetic workpiece, right? Due to the magnetic workpiece. Now, what happen if the arc flow will occur, my dear? Because of arc flow, there will be a low heat penetration. The effect is very simple. There will be a low heat penetration. Low heat penetration, right? Low heat penetration. The next effect is that excessive weld spatter. Excessive weld spatter. Okay, excessive weld spatter, right? And the third effect is that pinch effect in welding. The pinch effect in welding is the result of what? Is a result of electromagnetic forces. It is a very important. So I'm going to change the color. Pinch. Okay, pinch effect. Pinch effect in welding. In welding is the result. Pinch effect in the welding is the result of electromagnetic forces. Is a result of electromagnetic forces. Electromagnetic forces, right? Electromagnetic forces. So this is the effect of arc blow. We don't want a arc blow, right? We don't want a arc blow. Because of arc blow, there are, there are the things which is going to be happen. So this is the pinch effect, right? This is the pinch effect. Now, the effect of arc blow, how can you minimize the effect of arc blow? First of all, you should shorten the arc length. Whatever be the gap in between the electrode and workpiece, that gap should be what? Small. That gap should be small. So it get a minimum. Okay, the ions have to travel minimum length. In the minimum length, the deviation become what? Minimizes, right? Reduce the current. If you reduce the current, then magnetic field is also going to be reduced. If magnetic field is also going to be reduced, then the net magnetic force is going to reduce, which act on the ion, right? Third, welding speed. You should reduce the welding speed, because if you increase the welding speed, then the relative bending of the ions or relative bending of the arc will be more, right? Balance the magnetic field, because my dear, unbalanced magnetic field will be always there, right? Practically, you cannot completely eliminate the unbalanced magnetic field. So what to do? You have to balance the magnetic field by applying some external effects, right? Last, okay, you can just neglect this one. Okay, you can just neglect this one. Now, so this is up to that. Now let's move to the next topic, that is a gas shield. Gas shield basically what? My dear, gas shield basically an inert gas is blown into a weld zone. Initially, in the weld zone, there will be atmospheric gases, right, which is going to be ionized. But the disadvantage of atmospheric gases are what? They will react the weld pool. So that's why we recommend here inert gas, because inert gas are most stable and they are not going to react with the weld pool during welding. So an inert gas is blown into the weld zone to drive away other atmospheric gases. As I told you, other atmospheric gases are what? They have a tendency to react with what? React with the weld pool, my dear, right? So which type of gases we prefer here? We prefer argon, helium, nitrogen, carbon dioxide, and sometime the mixture of these gases, right? Sometime the mixture of these gases. Now here the first type of this is the welding, where this is the tungsten inert gas welding, where we use a inert gas. Okay, as the name reflects, tungsten inert gas welding. Tungsten means there is a non-consumable electrode. Okay, non-consumable electrode, and we are using a inert gas, right? We are using a inert gas. My dear, tungsten has a property. Tungsten has a very good property. What is the property of the tungsten? The tungsten basically, if in tungsten there is a alloy called as thorium and zirconium. Because of thorium and zirconium, the current carrying capacity or the current carrying or electron emission characteristic is what? Is improved, right? The current carrying and electron emission characteristic is what? Is improved. Okay, because of thorium and zirconium. Here we recommend what? Here we recommend a inert gas, right? Here we recommend a inert gas. Now, before go to the next slide, I just want to discuss about the electrode coating characteristic. Because why electrode coating characteristic? Before going to the gas shield, let me discuss electrode coating characteristic, right? Electrode coating characteristic. Okay, electrode coating characteristic. Okay, RIS characteristic, right? Electrode coating characteristic. Electrode coating characteristic. Now the first point. The first point is that, I mean, what do you mean by the electrode coating, my dear? There will be, you know, na, this is what? This is a electrode. This is what? This is electrode. And around the electrode, we are doing some what? We are doing some what? We are doing some coating. This is a flux, right? This is what? This is what? This is the flux. This is what? This is flux. So this is what? This is flux. That flux is known as what? Coated. A coated electrode. Now what should be the property of the coated electrode? Coated electrode should provide a, you know, the characteristic of the coated electrode is what? It should provide a protective atmosphere. It should provide the protective atmosphere, right? Should provide the protective atmosphere. Protective atmosphere, right? Second, my dear, stabilize the arc. Suppose if there is an arc below, it should stabilize the arc. It should minimize the arc blow, right? It should minimize the arc blow. It should control the cooling rate after welding. After welding, because when the flux cools down, it will deposit over the weld pool in the form of slag. After welding, basically slag should control the cooling rate. Right? Slag should control the cooling rate, right? I think this is more than enough, right? I think this is more than enough. Okay. So we have discussed, okay, gas shield, right? And also we have discussed what? We have discussed the tungsten inert gas, right? So let me take some important point in tungsten inert gas, okay? Or before the tungsten inert gas, let me discuss some important electrode coating, okay, electrode coatings, right? So just before that, this is electrode coating characteristic. So let me discuss one more thing. That is what? That is your electrode coatings, right? We have seen the electrode characteristic. Now we should know the name of electrode coating material. Electrode coating material. Electrode coating materials, right? Electrode coating material. My dear student, electrode coating materials, right? Electrode coating material. The first name of the coating is what? That is a slag forming ingredient. Slag forming ingredient, right? Slag forming ingredients. What are the slag forming ingredients? Basically like asbestos, calcium carbonate, right? Calcium carbonate, asbestos, okay, asbestos. So they produce a slag, right? There are a lot of other are also there. Second ingredient which we required is arc stabilizing agent. Arc stabilizing agent, right? Arc stabilizing agent. So in arc stabilizing agent, basically we required a potassium silicate, right? And second is TiO2 plus ZrO2, TiO2 plus ZrO2, O2, that is rutile, right? So this ingredient basically stabilize what? Stabilize the arc. The third ingredient is deoxidizing ingredient. Deoxidizing ingredient. Right? Deoxidizing ingredient. Basically, this deoxidizing ingredient remove any oxygen or any atmosphere which is present near the whirlpool like oxygen. So it is cellulose and calcium carbonates. Cellulose and calcium carbonate. Calcium carbonate. Right? And the fourth ingredient, right? The fourth ingredient which we required here is a binding material, right? Binding material. Binding material. Binding material. My dear, binding material like sodium silicate and potassium silicate. Sodium silicate and potassium silicate. Potassium silicate, right? Sodium silicate generally prefer with DC condition and potassium silicate generally prefer with AC condition, right? With AC condition, and some alloying element also you can prefer in the coating, right? Some alloying material also we can prefer in the coating, right? So I hope this point is crystal clear. Now here arc length should be stabilized, right? Arc length should be stable, my dear. Arc length, right? Let me discuss about little bit about the arc length. For good weld, okay, a short arc length is necessary. A short arc length is required, right? For a good weld, a short arc length is required. Why? If the arc length is short, then the heat is concentrated. Heat is concentrated, right? Concentrated. If the arc length is short, then then the heat is what? Concentrated. Second, the arc is more stable, right? The arc is more stable. Third, more protective atmosphere, right? More protective atmosphere. More protective atmosphere. More protective atmosphere means the gaseous shield which is produced due to the burning of coating, electrode coating, okay, it will produce what? A protective atmosphere surround the weld pool, which protect the weld pool, right? Which protect the weld pool. So this is some important thing. And you know what happen when a long arc is going to be produced, or if the gap is going to be produces, my dear, if the gap which is in between the electrode, this is the electrode and this is the workpiece, right? If this gap is going to increase, I need this is what? Shorter. We need this thing is what? Shorter. Because if this gap is going to be increased, this arc length is going to be increased, then larger heat losses into atmosphere. Second, unstable arc. Third, weld pool is not protected. Fourth, weld has low strength, less ductility, poor fusion and excessive spatter. That's why we required a shorter arc length, right? That's why we required a shorter arc length. So I hope the point is crystal clear to you people. So let's move to the our previous discussion, that is a tungsten inert gas welding. We have seen that in tungsten inert gas welding, what are the required thing? Basically in tungsten inert gas welding, basically, okay, we have seen there is a non-consumable electrode, okay, there is a non-consumable electrode, tungsten basically alloying with thorium and zirconium because it improves the current carrying an electron emission characteristic. Also, you may be surprised that tungsten is non-consumable. Then how the metal is going to be transferred from the electrode to the workpiece? My dear, if it is required, if the gap is large, then separately we take a filler rod. If the gap is small, if the gap between the base plate is small, then without using the filler metal, we can do the welding. But gap in between the base plate, okay, base plate is large, then we separately use a filler metal rod, right? We separately use a filler metal rod. Also here you will get a very clean weld, right? For welding all the material, for welding all the material, right, except aluminum magnesium alloy. But you may be asked, sir, in aluminum you told us that TIG welding is used. My dear, you have to change the polarity, right? You have to change the polarity, right? Then after you can do the welding. Generally what happen in TIG? In TIG generally straight polarity is used. In TIG generally straight polarity is used, right? I am talking about in general case. Generally, okay, please listen me carefully. Generally straight polarity is used, okay, with DC current, with DC direct current. My dear, if you take a straight polarity and if you use that TIG welding for aluminum, not beneficial. But if you change the polarity, right, if you change the polarity in case of aluminum, then the welding become very easy. And along with that, if you take a AC polarity, then the welding become very easy in case of aluminum. But in other case, but remaining rest of the metal is going to weld by TIG by using straight polarity, right? By using straight polarity. Okay, so let's move to the next point. My dear, here argon, here generally we use argon as a inert gas, okay, argon as a inert gas. So tungsten is a non-consumable electrode, and here it has a 100% duty cycle. So the tool is going to be heat up. So torch is water or air cooled, right? So the torch is water cooled, water or air cooled, right? So the torch is water or air cooled, right? So these are some important points. Please remember these points, right? So please remember these points. So let's move to the next point. Let's move to the next point. Gas metal arc welding. Yes, in gas metal arc welding, I mean, there is one more point we can discuss, like thermal diffusibility. But thermal diffusibility I will discuss later. First of all, I will discuss gas metal arc welding. Okay, that is MIG, that is metal inert gas welding. My dear, in metal inert gas welding, please listen me carefully. In metal inert gas welding, first of all, here we use a consumable electrode. Second, it is a automatically, because generally this is what automatic welding. So if you use a consumable electrode, it means the gap is going to be very, to maintain the gap between the electrode and workpiece, the automatic feed is required. Otherwise gap is going to be what? Changes. So automatically feed bare wire electrode. Here we use a mixture of gas or a simple gas, that is argon, helium, and sometimes mixture of these two gas can be used, right? Any metal can be welded, but use primarily with the non-ferrous metal. You can weld, okay, you can weld any metal, right? You can weld any metal, but generally it is used for non-ferrous metal. My dear, if you use direct current electropositive, yes, means reverse polarity. If you are using direct current reverse polarity, okay, then deposition of the metal become increases. Okay, deposition of the metal become increases, less arc blow, okay, less arc blow, right? Means if you use a reverse polarity with the DC current, then there will be more deposition of the metal and low and very less arc blow. But if you use a reverse polarity, if you use a straight polarity with direct current, then large arc blow will be happen, my dear. So if you want a straight polarity direct current in this welding, for this case you need a arc stabilizing agent. And straight polarity direct current direct straight polarity SPDC, that is what straight polarity direct current. SPDC generally prefer for non-ferrous, and you have seen that any metal can be welded but also used primarily with non-ferrous. In non-ferrous we prefer which polarity? We prefer, because non-ferrous metal don't have very high melting point, so generally we prefer DCRP or RPDC. Okay, you can say, you can write, oh sorry, yes, okay, yes, you can write RPDC, that is a reverse polarity direct current, right? In this case what happened? More deposition on the base plate, second, less arc blow, right? Less arc blow, smooth and very clean welding will be happen. But if you are doing SPDC, generally SPDC is required for ferrous metal. If you are doing welding of ferrous metal, if you are welding with ferrous metal, then in this case you need a SPDC, and if you use a SPDC, then there will be more arc flow. And if you want a minimum arc flow, if you want to minimize the arc flow, then in that case you need a arc stabilizing agent, right? Arc stabilizing agent. So this is the automatically feed electrode, you can see, so that the gap in between the electrode and workpiece is what? Maintained. The next welding is submerged arc welding, right? Submerged arc welding, my dear. So in submerged arc welding, a thick layer of granule flux, is deposited just ahead of a bare wire consumable electrode. What happened? Let me explain you with the help of figure. This is what? This is a bare wire electrode, and ahead of that there is a granule flux. This is what you can see in the figure. It is a granule flux, right? This granule flux, and ahead of this there is what? There is an electrode, okay, and that electrode is submerged in the granule flux. The electrode is going to be produce arc, okay, the arc is going to be produced in between the electrode and workpiece, and because of arc, what happened? The flux is also going to be consumed, okay. The weld pool is highly protective because it is surrounded by flux and the shielding gas, right? So that's why we call as a submerged arc welding, my dear. Here you have seen a bare wire consumable electrode we are providing here, okay. The arc is produced under the blanket of what? Under the blanket of granule flux. So you are not able to see the arc, right? You are not able to see the arc in a very easy manner. Here the weld pool is highly protected because over the weld pool there will be a granule flux and the atmospheric and the shielding gas which is produced due to the consumption of flux, right? Because of that, the weld pool is highly protected. That's why the cooling rate of weld pool is very slow. That's why we get here soft and ductile joint. We get here soft and ductile joint, right? We get here soft and ductile joint. So this is a submerged arc welding. Now let's talk about the gas flame process welding or cutting. Yes, by using a gas flame process you do a welding and you can do a cutting also as well as, my dear. Basically in a gas flame we generally prefer what? Oxy-fuel. Look, in oxy-fuel gas welding, what is the heat source? The heat source basically is the flame that is produced by the combustion of what? That is produced by the combustion of acetylene and your oxygen. So here your primary fuel is what? Acetylene. That acetylene is going to mix with what? That acetylene is going to mix with, right? That acetylene is going to mix with the oxygen, and combustion will take place in the mixture, and the heat is going to be what? Produces, right? So oxy fuel welding okay, has a largely been replaced by other process. But it is still popular. Why? Because it is cheaper and it is portable. You need only two cylinder. One is the fuel cylinder and one is the oxygen cylinder, and it is cheaper and portable. That's why still we are doing oxy fuel welding. Here the main fuel is what? Acetylene is the primary gas, okay, primary fuel gas employed. Right? Now, what is going to happen here? Suppose the mixture is going to be, okay, suppose here C2H2, that is acetylene plus oxygen. The mixture is prepared. This mixture is coming from the cylinder. This is the oxygen cylinder. This is the fuel cylinder. Okay. Now this mixture is going to the chamber, and from the chamber, okay, it is coming out through the nozzle. Through the nozzle, right? Through the nozzle. Now, a combustion is going to be happen. A combustion of oxygen and acetylene in a welding torch produce a temperature in two stages. In first stage, my dear, in first stage, what happened? Please listen me carefully. In first stage, C2H2 plus oxygen, okay, when you react, when you provide a heat, then carbon monoxide, okay, carbon monoxide, hydrogen plus heat is going to be produced. If you balance the reaction, then this is 2. Now, here you can see there is an incomplete combustion of the fuel. Heat is produces, but there is an incomplete combustion of what? Fuel. Now, this oxygen is coming from the cylinder. Now, in the second stage, carbon monoxide is going to react with again oxygen, and it produce carbon dioxide and heat, right? Carbon dioxide and heat. Carbon dioxide and heat. I'm not going to balance here. This is a second stage, and your hydrogen again it is going to react with oxygen and it produce H2O, that is a vaporized form, plus heat. Now this is a complete combustion. This is a complete combustion, right? If you balance it, okay, then you can balance this. This is 2 and this is 2. So 4, okay, 4 and 2, okay, hydrogen, that is half, okay, not half, that is H2O, right? Half H2 and O. So this is half, right? Okay, now see, this oxygen is not provided by the cylinder, it's come from the atmosphere, right? This oxygen will come from the atmosphere. Now, my dear, there are 3 types of flame which we get. There are 3 types of flame which we get in the in the oxy flame welding. The first type is neutral flame. The first type is neutral flame, right? Neutral flame. Neutral flame means the mixing of acetylene and oxygen are in the same proportion, 1:1, right? Or it is practically 1:1 to 1.15 to 1. So here the proportion is same. So neutral flame is going to be produced. Means in this flame, okay, you can see a flame. In this flame, neither excess of carbon and neither excess of oxygen is not present. Excess of carbon and excess of oxygen is not present, because they are present in the equal, because initially fuel and oxygen are in equal portion. So all the components are going to be what? Consumed here in the reaction. So this flame is not going to carburize, means addition of carbon, and this flame is not going to do any oxidation, means decarburization from the welding, from the base plate, right? So most welding is done with the neutral flame. It is chemically neutral. This flame neither oxidize, means this flame neither decarburize or carburizes the metal being welded, means neither there will be the addition of carbon and neither there will be the removal of carbon happens by using this flame. right? Because excess carbon is not there in the flame, so addition of carbon will not happen. That is oxidization or decarbonization. Excess of if excess of carbon is present, then what happen? Carbon is going to add into the surface. That is carburization, right? This is not going to be happen. Now here the temperature is very, very important. The innermost cone has the highest temperature, that is 3100 degree Celsius. Outer flame has a lowest temperature, but innermost cone has the highest temperature, that is 3100 degree Celsius. The welding is done by the innermost flame, right? The welding is done by the innermost flame. Now the second is your oxidizing flame, right? Your oxidizing flame. My dear, in oxidizing flame, basically proportion of oxygen is more than fuel, right? And here the ratio of oxygen to fuel is 1.5 is to 1, oxygen to fuel. This is the ratio. So that flame is known as oxidizing. That flame is known as oxidizing flame. Here the inner cone temperature, okay, having a highest temperature, that is 3300 degree Celsius. It is a hotter than neutral flame. Hotter than a neutral flame, about 3300 degree Celsius temperature is there, right? Okay, is there. This flame we used when welding some non-ferrous alloy. If you are welding some non-ferrous alloy, then you can use this flame. My dear, here in this flame, excess of oxygen is present. Excess of oxygen is present. If you use this flame for a ferrous material or a steel material, then what happen? The excess of oxygen are going to remove the carbon from the surface of the workpiece. So this flame is not recommended for a steel or iron based flame, because it will decarburize the welded material or the welding material, right? The welding material or the base plate. So harmful when welding steel, because the excess oxygen react with the carbon, decarburize the region around the weld. If you when the carbon is going to be removed, what happen? The hardness of that section is going to be what? Decreases, because carbon increase the hardness and strength, right? The next type of flame, that is the excess fuel. The next type of flame, that is excess fuel. That is excess fuel, my dear. Here excess fuel means proportion of fuel is more than compared to oxygen, right? So it produces what? It produces carburizing flame. Carburizing flame means percentage of carbon is more. Percentage of carbon is more in the flame. Unburned carbon is more in the flame, right? When you use this flame, then there will be addition of carbon into the welding, into the base plate, right? Into the welding plate. So the excess fuel, basically what? Here the excess fuel decompose carbon and hydrogen, and the flame temperature is not as greater, right, above the 3000 degree Celsius. So here the flame temperature is not so high. Here the flame temperature is not so high. The flame temperature nearly 2900 degree Celsius. It is not greater than 3000 degree Celsius. It is less than 3000 degree Celsius. So generally we use these type of flame, okay, in welding of molten material. Also it is also used for high carbon steel. High carbon steel. Why? We are not going to weld. We are going to increase the hardness of the high carbon steel. Sometime what happen in the hot forging? In the hot forging, decarbonization will be occur. After the hot forging, we use a carburizing flame, so that again we can increase the percentage of carbon, okay, of that forged product, right? So in that case we can use a carburizing flame, right? Now, oxygen torch cutting. My dear, by using similar flame, you can do a cutting operation also. Yes, you can do a cutting operation also. By using same flame, you can use a cutting operation also. The thing is, how? The question is, how can we do a cutting operation? Now, the answer is very simple. Basically, the answer is very simple. What happened? Iron, there is a basic fundamental which you have to remember. What is a basic fundamental? What is a basic important point? This first point is very important. Please remember this point. By using that property of iron and steel, we are going to cut iron or steel or ferrous material. By using that concept, we can cut steel and your ferrous material. My dear, iron and steel oxidize, right? When you heat it to a temperature between what? 800 to 1000 degrees Celsius. Oxidize means what? They burn, and their metal oxide has lower melting temperature. Suppose that there is a iron metal, okay, there is a iron. Now if you burn, okay, you provide a heat and oxygen, it will burn, it will produce iron oxide, right? And that iron oxide has lower melting temperature. That iron oxide has lower melting temperature than iron. So at less temperature, what happened? The oxide is going to be produced and it will remove, and the cutting is going to be what? Happen. Now, I will explain you what is going to be happen. Let me explain you this thing with the help of figure. Here you can see we are using oxy flame, okay, and we are using cutting. How is it possible? It is possible because of this thing. My dear, this is the tip of what? This is the tip basically of your nozzle when you are doing a joining process. From this is the tip of the nozzle, my dear. From here, the flame is coming when you are doing a welding, right? The flame is coming, the combustion flame, the mixture of the flame is coming when you are doing a welding, right? But when you do a cutting operation, the tip of the nozzle is this. This type of tip is used when you do a cutting operation. What is the difference? From here, and from here, the mixture of oxygen and fuel is coming, means, let me draw. The flame is coming, right? But from the center, along with that, from the center, my dear, a high pressure air is coming. So what is going to happen? When you provide heat to the iron along with oxygen, then iron is going to be what? Oxidize. It is going to be what? Burn, right? Then the oxide melting temperature is less than its own metal, so it is easily going to be what? Melt out and cut out. Very simple. Now the same concept I am going to explain here. This is basically a tip, right? This is basically a what? Just a minute, let me explain. Yes, see please. This is basically tip of the nozzle, my dear, right? This is a tip of the nozzle. Here at the periphery, there are a small hole. From that small hole, the flame is coming. And from the center, a fuel is coming, right? Oxygen is coming. From the center, oxygen is coming. A high pressure oxygen is coming. Okay, a high pressure oxygen is coming. Now this will do a cutting operation. So high pressure oxygen jet, right, which is at 300 kilopascal, is directed against a heated steel plate. The oxygen jet burns the metal and blow it away, causing a curve. That is cut, right? That is what? That is a cut. I hope you understood this thing. Right. Now, what is powder cutting? My dear, some of the metal like cast iron oxide have a higher melting temperature than its own metal. Remember what I am saying? Cast iron oxide having higher melting temperature than its own metal. Right. So in that case, we need a higher temperature. We need a high temperature. So in that case, we use a powder cutting. What is the powder cutting basically? Here in the powder cutting, let me explain you the powder cutting. Right. Let me explain you the powder cutting here. Let me explain you the powder cutting. This is a workpiece, right? This is a workpiece. Please see properly. See here. This is a workpiece. Now, you want to cut that workpiece like this workpiece, like it is a cast iron. Now, this workpiece is not going to cut because its metal oxide has higher melting temperature than its own metal. So, what we do, suppose you want to cut that surface, okay, along this line. Along this line, you are going to cut, okay, along this line you are going to cut. So, sprinkle, my dear, here you have to sprinkle the iron powder. Here you have to sprinkle the iron powder. This is what? This is the iron powder. This is what? This is the iron powder, my dear. This is what? This is iron powder. Right? This is iron powder. This is iron powder. Now next you have to provide the same type of flame. Right? Next you have to provide the same type of flame. Right, you have to provide the same type of flame. What happened? My dear, if you provide same type of flame, then temperature is going to be increased, right? The cast iron is going to be burned, and because of extra iron powder, what happened? You know, when iron is going to be burned, it do a exothermic reaction. When this iron is going to be what? When this iron is going to be burned, that extra powder is going to be burned, it produces a exothermic reaction. That is more temperature, my dear. That is what? That is more temperature. Please remember what I am saying. It means more temperature, right? More temperature. Yes, more temperature. It do a exothermic reaction, and because of that exothermic reaction, the metal is going to be what? Melt out, right? The metal is going to be what? Melt out. Because of this iron, when it going to be burn, it do a exothermic reaction. Exothermic reaction. And because of exothermic reaction, extra heat means that extra heat will melt cast iron oxide. If that cast iron oxide is going to be melted, then this portion is going to be what? Cut. Right? So this is the powder cutting, my dear. So this is the powder cutting. Right? Next topic is resistance welding, my dear student. Next topic is resistance welding. Right? So let me write down resistance welding. Resistance welding. This is our next topic. Now let's see. Basically, resistance welding, what we are going to do, we are going to use both heat and pressure. Here we use both heat and pressure, okay, for the welding. So both heat and pressure are used. So it is written there. I know it is in the red color, so it is not visible to you. So I'm going to write it again. Here, basically the principle is both heat and pressure are used for the welding, right? Here what we do, here heat is going to be generated, okay, in between the workpiece. Let me show you. Here This is your workpiece, my dear student. This is your workpiece, right? This is your workpiece. See here. This is the workpiece. This is my workpiece. Okay, which are placed in an overlap position. See here. And here, this is the electrode, right? This is the electrode. See here. So, this is the electrode. With the help of electrode, basically what we are going to do, we are going to apply a pressure. We are going to apply a what? Apply a pressure, right? Now, apply a pressure. Along with that, we supply the current. Current is also go. And at the interface, the heat is going to be produces. Okay. So, heat is generated by the electrical resistance of the workpiece and the interface between them. Maybe you can ask that, sir, there is a resistance of the electrode also. There is a resistance in between workpiece and electrode also. There is a resistance of there is a resistance of this interface also. My dear, these resistance are what? These resistance are very small compared to the resistance of what? Interface. Basically, the maximum resistance will appear or will be available at the interface of the workpiece. So that's why when the current is passing through with the time, then more heat is going to produce at the interface. And what happened? Because of that heat, the interface is going to be what? Melt, right? And by applying the pressure, these melting zones are going to fuse to each other, right? Are going to fuse to each other. Here we are applying the pressure. Here we are applying the pressure. That's why the required amount of heat is less if you compare to what? Oxyacetylene fuel welding, right? If you compare with the oxyacetylene fuel welding, because here we are applying pressure along the current. So due to pressure, a lower temperature needed, right? Due to pressure, lower temperature needed, my dear student. Lower temperature is what? Needed. If you compare the oxyacetylene, okay, welding, right? Now, here you can weld a dissimilar metal also, because you are applying a lot of pressure here. My dear, this interfacial resistance is in the order of micro ohm, right? Micro ohm. Are you getting my point? Means 10 to the power minus 6 ohm. 10 to the power minus 6 ohm. So this interfacial resistance is small. So here you can get one thing, that by applying, my dear, here by applying a small voltage, you can supply a large amount of current. So very low voltage, because of this interfacial resistance is very low. So at very low voltage, we supply high amount of what? Very high current, right? Very high current, my dear. Very high current we are going to what? Supply, right? At very high voltage, we supply very high current. Am I clear? So you will be observed that very low voltage means in the up to the order of what? Up to the order of 10 volt. Up to the order of 10 volt. And very high current, that is up to the order of 1 lakh ampere, or maybe this is a maximum. This is a maximum, my dear. Below 1 lakh means 10,000 ampere, 5,000 ampere, that much amount of current you can easily flow by using that much voltage or below that voltage. Am I clear? So in resistance welding, it is a characteristic. Please remember that very overall resistance is very low. I told you how much overall resistance will be 10 to the power minus 6 ohm. So this is a very low resistance, and because of very low resistance, very high current you can flow at a very low voltage up to the order of from 0.5 to 10 volt. right? So this is the key feature. Now there is a question. Before that question, I will explain you one more thing, that here when you are doing a welding, my dear, suppose that when we are doing a welding, right, let me explain you few more thing. Let me explain you few more thing. Okay, let me make a copy of this. Yes, my dear student, what we call this joint, this fusion zone, right, this fusion zone, this is what, this is a fusion zone, this is a fusion zone, right, this is a fusion zone. Very small amount of material melt, or you can say fuse to each other. Fusion, very small amount of material do a fusion, a small amount of metal or material fuse to each other, right, or melt to each other. Now, so this zone is also called as nugget. The technical name of this zone after solidification we call as nugget. My dear, here you can see a nugget of oval shape. Okay, here you can see that the nugget is oval shape. It is not necessary that always be the nugget in oval shape or elliptical shape, right? The shape of the nugget may be spherical, right, may be cylindrical, right. So the shape of the nugget may be vary, right, the shape of the nugget will vary. This shape of nugget will be decided by the projection welding, which we are going to discuss in the upcoming slide. Okay, so this is the nugget. It may be a spherical, it may be a cylindrical, or it may be a what, oval or elliptical shape. Oval, or you can say a elliptical shape. The best word for that is elliptical shape. This is what, elliptical shape. Elliptical shape, right, this is the elliptical shape, and the nugget may be of the spherical and maybe of the okay, cylindrical shape. Now let's move to the question. Before question, let me tell you how much heat is going to produce here. The heat which is going to produce, or the heat which you are giving as an input, right, heat, HI stand for input heat. Input heat which you are giving is what, I square, I the amount of current which is passing through, R is a overall resistance at the interface, T is the time up to which you are passing the current, that much joule, right, that much joule heat you are giving as a input. But how much heat is utilized, because some of the heat is going to waste in the workpiece, right? So required heat or the actual heat, HA stand for actual heat required. Actual heat required. Actual heat required. Okay. Suppose that if you know the mass of the nugget, suppose that if you know the mass of the nugget, Mn stand for mass of nugget, right? You know the mass of the nugget. Okay, you know the specific heat, right? Specific heat of the plate. You know the latent heat of the plate. You know the melting temperature of the plate. You know the initial temperature of the plate, my dear. Now, if you know all the thing, then the heat required to produce that nugget will be what? Mass of the nugget, C, specific heat of the plate into change in temperature plus mass of the nugget into what? Into latent heat. So this is what? This is the overall overall actual, basically actual heat. So the welding, the efficiency is what? Welding efficiency or melting efficiency, melting efficiency, melting efficiency, efficiency, because every time the gate, in gate, this type of question will be asked. So the melting efficiency will be, my dear, that is actual heat divided by the heat which is, okay, which you are giving as a input, right, which you are giving as a input. Am I clear? Is that point is clear? I hope the point is crystal clear, right? The point is crystal clear. So on this basis of this concept, we are going to solve some of the numericals. Okay, please see the numerical here. This question was asked in 2007, right? This question was asked in 2007. Please see the question. Okay, maybe the question is not visible to you. I will try to magnify it. Not this. Okay, now I will read it out. Please pay attention what he says. Two metallic sheet, each of 2 mm thickness, each of 2 mm thickness, means what is that? There will be two metallic sheet, right? There will be two metallic sheet. This is this is a metallic sheet. This is a metallic sheet, right? And each has how much thickness? 2 mm. Each has how much thickness? 2 mm, right? 2 mm. Okay, now let's read again. Are welded in a lap joint configuration by resistance spot welding at a welding current of 10 kilo ampere. How much current we are using here? We are using, okay, we are using 10 kilo ampere current. 10 kilo ampere current, right? And welding time of 10 millisecond, and welding time is 10 millisecond. Welding time is 10 into 10 to the power minus 3 second, right? This is the welding time. A spherical fusion zone, a spherical fusion zone extended up to the full thickness of each sheet is formed. My dear, he is saying there is a spherical fusion zone. Is that fusion? Is that spherical fusion zone he is talking about? No. He is saying a spherical fusion zone extended up to the full thickness of the sheet. Means a spherical fusion zone like that. A spherical fusion zone of like that is going to be produced, right? So this spherical fusion zone have a radius of what? Have a radius of 2 mm. Am I clear? So this is the spherical fusion zone, right, which is extended up to the full thickness of the sheet. Now ambient temperature, that is room temperature, is given. Okay, ambient temperature, that is T0, is given 293 Kelvin. Melting temperature is given, that is 1793 Kelvin. Latent heat is given of the plate, that is 300 kilojoule per kg, and density is given of the plate. Density of the plate is what? 7000 kg per meter cube, and specific heat is given. What is specific heat? 800 joule per kg Kelvin. The contact resistance along the sheet interface is 500 micro ohm. He says that contact resistance means what? The contact resistance between the plate. He says it is a 500 micro ohm. Along the electrode and sheet interface is 0. Along the electrode, whatever be the electrode is there, right? Whatever be the electrode is there. Okay, that contact resistance is what? That contact resistance is 0, right? That contact resistance is what? 0. The resistance which he considering is the interfacial resistance, that is 500 micro ohm, right? Now, okay, you have to find basically a melting efficiency. Here 500 micro, that is 10 to the power minus 6 ohm is given, and you have to find, my dear, melting efficiency. I hope the question is crystal clear. Now you need to calculate how much input heat you are giving. So input heat is I square RT, right? I square RT. So we know that the value of I here, we know that the value of I, that is 10 kilo ampere. So the 10 kilo ampere, 10 into 10 to the power 3 square, resistance 500 into 10 to the power minus 6, and time, that is 10 into 10 to the power minus 3 joule, right? That is what? That is input heat. That is what? Input heat. So it is 10 into 10 to the power 3 square into 500 into 10 to the power minus 6 into 10 into 10 to the power minus 3, right? It is coming 500 joule. So input heat is what? 500 joule. Now the actual heat, we need a actual heat, but for actual heat I want to know the mass of the nugget. So mass of the nugget is what? That is volume of the nugget into density of the plate, right? So what is the volume of the nugget? My dear, volume is what? Volume is sphere. So mass of the nugget basically 4 by 3 pi r cube, pi r cube, right? This is the volume of the nugget into density of the plate. Also here you can write that 4 by 3 pi, r is what? 2 mm. So 2 into 10 to the power minus 3 meter cube. Density of the plate is what? Density of the plate is 7000 kg per meter cube. So 7000 kg per meter cube. So you will get the mass of the nugget. So 4 by 3 into shift pi into r, that is 2 into 10 to the power minus 3 cube. Okay, so cube into 7000, that is 2.345 into 10 to the power minus 4 kg, right? Minus 10 to the power minus 4 kg. Now you know the mass of the nugget. So now you have to calculate actual heat which we are giving. So actual heat is mass of the nugget, specific heat of the plate, change in temperature, plus mass of the nugget into latent heat. Here mass of the nugget is common, so I am taking mass of the nugget common into specific heat, change in temperature, plus latent heat, right? So mass of the nugget is 2.345 10 to the power minus 4, okay, into specific heat. What is the specific heat? Specific heat is 800 joule per kg per Kelvin. So 800, right, into your, what is the delta T? That is 1793 minus 293. 1793 minus 293, right? Plus what will be the latent heat? Latent heat is 300 kilojoule. My dear, it is 300 kilo. So 10 to the power 3. So this is the actual heat which is coming. So what is that? Answer into 800, 3 and 0 and 7, 800 into 1500 plus 300 into 10 to the power 3 So it is coming 351.85 joule. So what will be the melting efficiency? Melting efficiency is your actual heat divided by input heat. Actual heat is what? 351.85 divided by 500. Divide by 500. Answer divide by 500. It is coming 0.7037. But you need in a percentage. So multiply this answer by 100. So you will get 70.37% in terms of percent. So here answer C, option C is the correct answer, right? Now let's solve the next question here. Resistance spot welding of two steel sheet is carried out by a lap joint configuration by using a welding current of what? Here welding current I is 3 kilo ampere, 3 into 10 to the power 3 ampere, and a welding time that is what? 0.2 second, right? A molten melt nugget of the volume here nugget volume is given, that is 20 mm cube is obtained. The effective contact resistance is 200 micro ohm. The effective contact resistance is 200 micro ohm, that is 200 into 10 to the power minus 6 ohm. Okay, the material property of the steel are given. Latent heat is given. Okay, latent heat is given, density is given, melting temperature is given, specific heat is given, the ambient temperature is given. Used for producing weld nugget, heat used for producing the weld nugget will be. So you have to find out, my dear, you have to find out basically what? You have to find out, yes, you have to find out basically what? You have to find out here H actual. You have to find out H actual, right? H actual, right? This is the thing, because he wants to know heat used for producing a weld nugget will be. So mass of the nugget C into delta T plus mass of the nugget into latent heat. But in this question, specific heat is not given. So mass of the nugget into, I think specific heat is given. Specific heat is given. Yes, specific heat is given. So you can make it 0, right? You can't make it 0. So first of all, we have to calculate the mass of the nugget. So let's try to calculate mass of the nugget. So mass of the nugget is volume of the nugget into what? Density. So volume is what? Volume is given to us here, that is 20 mm cube is obtained, and density is given. Density, what is the density? Is the density is provided to us? Yes, 8000. So first of all, you have to convert 20 mm cube, right? 1 meter equal to 10 to the power minus 3. Okay, 1 mm equal to 10 to the power minus 3 meter, but it's a cube, so multiply it by 3 into what? 8000. So it will be come in kg. So mass of the nugget will be 20 into 10 to the power minus 10 to the power minus 3 to the power 3 into 8000, 1.6 into 10 to the power minus 4 kg. That is what? Mass of the nugget, right? This is mass of the nugget. Now actual heat which is required, mass of the nugget, take it common, specific heat, change in temperature, latent heat, right? So mass of the nugget 1.6 10 to the power minus 4 specific heat. So here the specific heat is what? Specific heat is 0.5 kilojoule and 1400 kilojoule, 0.5 and 1400, right? And change in temperature 15, 20, and T naught is what? Melting temperature is what? Or change in temperature is what? 15, 20 minus 20. So it comes what? 1500, right? Degree Celsius or Kelvin, right? 1500 degree Celsius. If you convert in a Kelvin, then you will get in a Kelvin answer, right? Okay. So Kelvin or degree Celsius, right? So 1500, 0.5 is a specific heat, and latent heat is 1400 kilojoule. 0.5, 0.5 into 1500 plus 14, okay, 100, both are in kilojoule, so multiply it, 10 to the power 3, that much joule is required. Answer into 0.5 into 1500 plus 1400, answer into 10, 10, then 344 joule. So actual heat which is required is 344 joule, right? So this is the type of question. I hope you understand this basic idea. Now suppose that in the same question, if he asks how much heat is going to be lost, how much heat is going to lost to the base plate. Suppose that if he asks how much heat lost to base plate, right, to base plate, then how can we find? Basically we have to find delta H, that is whatever heat you are providing or whatever heat is required, right? So you need a HI. So what is a HI? HI is what? I square RT. I is what? I is given. I is what? That is 3 kilo ampere. So 3 into 10 to the power 3 square, and resistance is what? 200 micro ohm, right? 200 micro ohm. So 10 to the power minus 6, and time is what? 0.2 second. Time is what? 0.2 second, that much joule. So this is the heat input. So this is the heat input, 3 into 10 to the power 3 is square into 200 into 10 to the power minus 6 into 0.2. So 360 joule we are giving. So what is the lost heat? That is 360 into 344, right, into 344. So 360 minus 344, it comes 16 joule. It's going to be waste, it's going to be consumed by the base plate, right? 16 joule is going to be consumed by the base plate. Now let's move to the next part, that is the resistance seam welding. Now what do you mean by the resistance seam welding, my dear student? Weld is made up of basically overlap, right? Here overlap sheets of metal are there, overlapping sheet of metal, right? Overlapping sheet of metal are there. They are overlap, they are placed in the overlap position, and what to do? Here a series of overlapping spots are going to be formed like this. Suppose that there is a please see, there is a overlap sheet, right? There is a overlap sheet, this is a overlap sheet, okay, and there will be a rotating disc like that, okay, there will be a rotating disc like that. Instead of electrode, they are rotating, right? They are rotating, and the current is supplied through the disc, okay, and the pressure also. So the overlap joint are going to be what? Formed. So the overlap joints, a series of overlapping joints are going to be what? Formed here, right? So the series of overlapping joint. So here a series of, I am going to write here, series of overlapping spot or nugget, okay, are going to be formed here. So here the basic equipments are same. Instead of electrode, there are what? Rotating disc. So equipment is same as for the spot welding, except the electrodes are what? Rotating disc. Here instead of electrode, there will be what? Rotating disc. There will be what? Rotating disc, my dear. There will be a rotating disc, right? There will be a rotating disc. All the equipments, I am going to write here, all the equipment is the same as for spot welding, as for spot welding, except that the electrodes are now in the form of what? Rotating disc. Clear? Rotating this. So I hope this clear, this point is clear. Okay, this is a rotating disc, this is a rotating disc, right? And this is what? Overlap joint. Overlap joint. Overlap joint. All the equipments are same. Instead of electrode, there is a rotating disc. Now, what is the projection welding? My dear, in the spot welding, before discussing the projection welding, let me discuss you a spot welding. Again, I am going to discuss a spot welding. My dear, in a spot welding, generally what is going to be happen? You are getting only one spot. Please see, you are getting only one spot. This is your electrode. Oh, sorry, this is your workpiece, and this is your workpiece, right? This is the electrode, right? And see here, this is your electrode. Now, where the electrode is going to apply the pressure, only there you will get only one joint. Only there you will get only one spot, right? There will be a one spot or one nugget, one joint, one spot or one nugget or one joint you are getting. Suppose I want a multiple nugget at a one time. Suppose that I want a multiple nugget at a one time, so I will use a projection welding. In projection welding, basically what we are going to do in projection welding, let me explain you. In projection welding, right? In projection welding, basically in projection welding, what we are going to do basically, in projection welding, we are going to produce our projections on one plate, right? On one plate, my dear. This is the, okay, one plate, and this is the projection which I am going to, yes. So this is the projection, this is a plate, right? This is a plate, and here I am producing a, this is a plate, right? Now, on this plate, we are going to make some projections. Okay, whatever shape you want to require. These are the, my dear, projections, right? These are the projections. See, these are the projections, and these projection basically, the projection, the base of this cone are here, right? Similarly, there will be a projection like this, right? There will be a projection like this. Now it is not visible because it is just behind that. The base of this cone is here, the base of another cone is here. Now, if you see, this is a 3D figure now, this is a 3D figure. If you see this figure in a two-dimensional way like this, then you can see only this projections. You can see only this projection. You can see only this projection, my dear. You can see only this projection. Am I clear? Now you are going to place this plate. Now you are going to place this plate over another plate. Okay, and a similar type of electrode we are going to see. This is my electrode. This is my electrode, and this is my electrode which I am placing here. A large electrode I am going to place here. Okay, and now current is going to be supply. Okay, current and pressure, right? Similarly, pressure is going to be supply. So what happened? At a one time you will get a multiple nugget. At a one time you will get a multiple nugget, my dear. At a one time, okay, you will get a multiple nugget, not a single nugget. You will get a multiple nugget. Am I clear? You will get a multiple nugget. See, at a one time you will get a more than one nugget. As many as projection is there, as many as nugget you will get, okay, in the projection welding. Now the next welding is your upset welding. Upset welding is what? Upset welding. In upset welding, basically here generally we produce a butt joint. There is here we produce a butt joint. What we are going to do here, pieces are held tightly. Whatever whatever joint we are going to make, whatever the joint we are going to make in between the workpiece, that pieces or that workpiece, that pieces are held tightly and current is applied, right? You are holding it tightly and current is applied. Because of current, interface, at the interface maximum heat is going to be produced, and because of the pressure the joint is going to be formed, right? Due to the pressure, suppose that this is the piece which you hold tightly, this is a piece, right? Another piece, this is another piece. Now you hold it tightly, you are applying the pressure and you are applying the current. Now what happened? Current and pressure, because of current and pressure, what happened? The heat is going to be produced. Now because of pressure, some of the metal will go in outward direction, that's why it is called upset welding, right? That's why it is called upset welding. Because of resistance, the heat is going to be what produces, right? Because of the interfacial resistance, the heat is going to be what produces. Here it is necessary that useful for joining rod or similar pieces. Here similar type of workpiece are going to be what joined, like what, like the example is what, rod, right? Like the example of what, rod. Next is, my dear, flash welding. Flash welding is similar to offset welding. Yes, flash welding is similar to offset welding. The only exception is that, except the arc is going to be produced, the arc, rather than resistance heating. Here arc is going to produce the heat. Now what is the thing? Basically there is the workpiece, right? This workpiece is hold tightly from here. Here I am going to hold this workpiece tightly, right? Now there is another workpiece. Okay, there is another workpiece, my dear, there is another workpiece which is attached to the cam and follower, and because of the cam and follower, the workpiece can move, right? The workpiece can move in forward and backward direction because with the help of cam and follower. All of you know about the cam and follower. You have a little bit learned in theory of machine. So because of cam and follower, the workpiece will move in forward and backward direction. Now when the workpiece comes in a contact with the electrode, then what happen? It is going to separate. When it going to be separate, my dear, right, the arc is going to be produced in between the interfaces. And because of the arc, the heat is going to be produces. Once the required amount of heat is going to be produced, then with the help of cam and follower, this workpiece, my dear, this workpiece will come in forward direction. Right? This workpiece will come in forward direction, and we are going to apply what? We are going to apply a pressure, right? And because metal is soft at the interface, so it will go in outward direction. So it is just like upset welding, right? Joint is just like upset welding. The only except that arc is produce the heat, okay, instead of resistance heating, right? Now let's move to the next heating, that is a percussion welding. In percussion welding, it is similar to the previous welding. What is the previous welding? Your flash welding. So percussion welding is similar to the flash welding. The only thing is that here, first of all, we are going to store all the energy in the capacitor. We are going to first of all charge the capacitor with the desired voltage. Then the capacitor will discharge the voltage, and when the capacitor will discharge the voltage, then the arc is going to produce in between the electrode, and once the required amount of heat is going to be produced in between the electrode, then the electrode will go in the forward direction, comes in a contact with the another electrode on another workpiece, arc will stop, and because of the pressure, molten metal will go in the outward direction, and the joint will be look like as a upset welding, right? But the movement of the molten metal is very less in this case. So it is similar to flash welding except arc power. What do you mean by the arc power? The arc power, basically here we are using a capacitor. This capacitor is going to first of all charge with the supply voltage V0, and that charge capacitor is going to be discharged, and when the charge capacitor is going to be discharged, then the arc is going to be produced in between the workpiece, right? So rapid discharge of stored electrical energy. The arc duration is only, the discharge time is only 1 to 10 milliseconds. So a very concentrated heat is going to be produces, okay, not more than required or not more than less. An optimum amount of heat will be available at the interface. Okay, this is a very good advantage of the percussion welding. Now let's discuss with the other welding technique, my dear student. In the other welding technique, a theoretical question will become in this section from your gate exam. So let's discuss one by one in a very hurry, in a very very fast manner, because a theoretical question may be asked or may not be asked, but we have to prepare for a theoretical question also, which carry a 1 mark, right? So first welding is a thermit welding. My dear, in thermit welding, what is there? Basically in thermit welding, there will be a box, right? There will be a box, right? Basically thermit welding is very popular in the joining of railway track. Suppose that this is my railway track, and above the railway track I have placed a box. In that box, what is there? There is a chemical mixture. There is a mixture. What? Metal oxide and metallic reducing agent. There is a metal oxide. There is a chemical reaction between metal oxide and metal reducing agent. Metal reducing agent. Metal reducing agent. Right? Metal reducing agent. Metal reducing agent. Now a spark is provided. Now because of spark, what happened? There will be a reaction between metal oxide and metal reducing agent, right? Like Al2O3. Okay, example is metal oxide is like Fe3. Metal oxide is Fe3O4, and metal reducing agent is what? Aluminium, right? Metal reducing agent is what? Aluminium. Now if you provide a spark, then what happen? A reaction will be happen. That aluminium, okay, that aluminium react with Fe3O4 and it produce Al2O3, right? If a reaction goes in between that, then Al2O3 is going to produce, basically this is a slag, okay, plus iron is going to be produced, but it will be in the liquid form, right? It will be in the liquid form, plus heat is going to be produced. A very large amount of heat is going to be produced within a very small amount of time. Nearby 3000 degrees Celsius is is going to be produced within a 25 second, my dear, within a 25 second. Okay, so this molten iron will come in between the gap, this molten iron will come in between the gap, and the slag, slag have a less density, so that slag have a less density, so that slag will come over the weld pool, right? Over the weld pool. So my dear, this is what? This is Al2O3, and this is what? This is your molten iron. Once the joining is going to be performed, once the joining is done, after the joining we do a finishing operation like grinding. By using a grinding, we remove the Al2O3 and the unnecessary upsetting, okay, on the track. So this is your what? This is your thermit welding, very famous in joining of the railway track in the remote location. It is basically used in the remote location. Next is your electro slag welding. Generally electro slag welding is used to join a very thick section. Yes, I'm correct, to join a very thick section. So let me explain this. To join a very thick section, okay, to join a very thick section. So let me draw a diagram here. Suppose that this is the workpiece which you are going to join. This is the workpiece which we are going to join, right? That we are going to join. Look, this is a thick section. This is a thick section, right? At the base, we are providing a base plate, right? At the base, we are providing a base plate. Now there is an electrode which is going to touch the starting plate. This is a starting plate, my dear. This is a starting plate. Starting plate, right? This is a starting plate. Now the electrode is going to touch. Now the electrode is going to touch this base plate and it is going to separate. Okay, not only one electrode, there will be a multiple electrode, right? There will be a multiple electrode. Not only one electrode, there will be a multiple electrode. One of them will act as a slag, one of them will act as a filler metal, right? So the arc is going to be produced in between the electrode. Arc is going to be produced in between the electrode, and the molten metal will fill in between the gap, right? In between the gap. There is another electrode also. This is another electrode. Maybe this electrode will provide a slag. So instead of one electrode, we use a multiple electrode because the gap is very large. So this large or thick gap is going to be filled by number of filler metal along with the slag electrode, right? Generally, this type of welding is used to join a thick section, like thick section in like a ship. Okay, to weld a ship wall, generally we preferred a electroslag welding, right? Electroslag welding. So I hope this concept is very crystal clear. Now let's move. This is the next figure. You can see, right? You can see this is a filler metal. This is a filler metal, which this is a molten metal, which is produced from the filler metal, and this is what molten slag. Why molten slag is on the top? Because the density of the molten slag is less if you compare the density of the molten metal. That's why it will be always available at the top, at the above of the molten metal. Okay, so electrode will move in upward direction. Okay, or you can say when the electrode is melting, so the gap is increasing, or a molten metal is going to fill in the gap. Now next is electron beam welding. It's a very simple thing, is that there is a vacuum chamber. All of you know that there is a vacuum chamber, my dear. There is a vacuum chamber and there is a tungsten filament, right? There is a tungsten filament. It is act as a cathode. This is a workpiece which is placed at the work table. This is a work table, right? This is the work table. This is the work table. Now this workpiece will act as a positive. Now a potential difference is going to be applied with the help of vacuum instrument. We are going to remove all the air, all the atmosphere. So it is a vacuum chamber. Okay, now potential difference is applied. Now there is one more thing. There is a coil. There is a magnetic coil. Basically this magnetic coil will focus the beam of electron toward the workpiece. Okay, the electron beam is going to be focused with the help of what? Magnetic coil, right? This is a magnetic coil. This is a magnetic coil which produce a magnetic field, and because of that electron beam is going to focus on the workpiece. When the electron will strike to the workpiece, its kinetic energy is going to be convert into the thermal energy, and because of the thermal energy the workpiece is going to be what? Weld. Generally electron beam welding will use in a electronic industry, where a very small circuit are going to be joined. Okay, because in electron beam welding, because by using electron beam welding you are not going to join a very large workpiece. With the help of electron beam welding we join a very small, we produce a very small weld pool, okay, in a small workpiece, right? So that's why electron beam welding generally prefer in a electronic industry. Laser beam welding. Laser is what? Light amplification, stimulation, emission, radiation. That high intensity beam will be focused onto the workpiece with the help of lens, and the intensity of the beam is 10 kilowatt per centimeter cube. So the intensity is so much high, my dear. The intensity is what? So much high. So that's why because of high intensity beam produces a very thin column of what? Of vaporized metal, with a surrounding liquid pool. A very thin column, very thin molten column is going to be produced. Here the penetration is more than the width of the weld pool. So depth to width greater than what? Greater than 4:1. So depth to width ratio is greater than 4:1, my dear. Now the next is friction welding. Maybe a numerical question will be asked in the friction welding. What is friction welding? Let me explain you with the help of figure. Basically, there is a one workpiece. Okay, there is a one workpiece. It is fixed, right? It is fixed. This workpiece is fixed. This workpiece basically is fixed, right? This workpiece basically fixed. Now, the another workpiece is attached in what? In the chuck. This is chuck. Now, because of the chuck, the workpiece is rotating with the high RPM. Now, it comes in a contact. Now, because of the friction, heat is produced in between the at the interface of the workpiece. Now, when the sufficient amount of heat is going to be produced at the interface, then all of a sudden the RPM is going to stop and we are going to apply a large pressure. The pressure is applied till the joint is not going to be what? Solidified. Because of that, what happened at the interface, liquid metal will go in the outward direction and it look like a upset welding, This is a friction welding. Here friction and pressure, here the friction and pressure is going to be applied. Like now in ultrasonic welding, my dear, I told you ultrasonic machining. So similar instrument are going to be used in ultrasonic welding also. Transducer, remember transducer? What transducer do? Transducer will produce a high ultrasonic frequency, and there is a tool holder concentrator. What it will do? It will magnify the amplitude, and below the concentrator or tool holder we are going to hold a workpiece, and that workpiece is going to be vibrate with the ultrasonic frequency and high amplitude over another workpiece. Because of this high vibration, okay, a large heating is going to be produced over the workpiece, and because of the heating at the interface, heat is going to be what? Produces, my dear. So a joint is going to be what? Produced. Let me explain you this, my dear. What is going to be happen? There is a transducer. There is what? There is a transducer. Please see. There is a transducer. This is a transducer. You know transducer. Transducer. This transducer produce ultrasonic frequency. And below that there will be a tool which is known as tool holder. Sometime we call as concentrator. What it do? Magnify the amplitude frequency. Magnify the frequency of amplitude, right? And below that there is a workpiece. Right? Below that there will be a workpiece. Now it will vibrate with a high frequency and amplitude over the another workpiece. And what happen? At the interface, large amount of heat is going to be produced, and the joint is going to be what? Happen. My dear, in ultrasonic frequency, we are not going to supply any current in between the or across the workpiece, right? So by this welding, you can join a metal and non-metal. Okay. So what happens? Suppose that it is a non-metal. Suppose that this is what? This is a non-metal, right? And suppose that it is what? It is metal. So what happened? Because of hitting of the metal over the non-metal, a heat is going to be produced. This metal is going to soft at the interface, and because of pressure, along with that we are going to apply a pressure also. Because of pressure, the soft metal is going to stick over the non-metal surface, right? Over the non-metal surface. Now the next one is brazing and soldering. My dear student. So let's see brazing and soldering. In brazing and soldering, basically what we are going to do in brazing, okay, let me explain you with the help of example. Whether you do a brazing, suppose that this is my base plate. Okay, this is my base plate. Now this is my base plate, right? This is my base plate. right? This is my base plate, right? This is my base plate. So in brazing and soldering, basically we are going to melt the filler metal. Okay, there is a gap. This gap is going to fill by the filler metal. Filler metal. That filler metal has a different composition. Okay, the filler metal has a different composition if you compare with the base plate, right? Right. So brazing is basically a joining of metal. Brazing is what? Brazing is basically a joining of metal through the use of heat and filler metal. Through the use of heat and filler metal, whose melting temperature, the filler metal melting temperature is above than the filler metal. This is a filler metal whose melting temperature is above than what? 450 degree Celsius. 450 degree Celsius. Now what happen if the melting temperature is 450 degree Celsius? Okay, but the base plate, let's say the base plate melting temperature, this is a base plate melting temperature. Okay, I'm going to write here. Please see carefully. My dear, please see carefully. The melting temperature, okay, the melting temperature of the filler metal. This is a filler metal. F stands for filler metal, right? And M stands for melting temperature. Is above than 450 degree Celsius. But it is less than base plate, okay, melting temperature. So here, at that temperature, base plate is not going to melt. Only the filler metal is going to be melt, and it will fill into the gap by capillary action. By capillary action, right? By capillary action. So if you compare welding with the brazing process, the joint is not strong as compared. The joint is not strong in brazing if you compare with the joint of welding. Why? Because here no fusion will take place. No fusion will take place because base plate is not going to be melt. So the composition of the brazing alloy, why the base plate is not going to be melt? Because the composition of brazing alloy, the composition of the filler metal is significantly different from the base plate. That's why base plate are not going to be melt. Fusion is not going to be happen. So if the fusion is not going to be happen, the strength will not come. The strength will not come if you compare the joint with other welding process, with other fusion process, right? So how a metal will go inside the gap? Because of the capillary action, the liquid metal will go inside the small gap. Now what is the soldering? My dear, here in the soldering, the thing is same. Thing is not going to be changed. This is a base plate. This is a base plate, my dear. This is a base plate. See, this is a base plate. Now we are supply the filler metal. This is a filler metal, right? This is a filler metal. Now here the filler metal melting temperature is less than 450 degree Celsius, right? Also melting temperature of base plate is greater than what? 450 degree Celsius. So here also the base plate is not going to be melt. Here also the base plate is not going to melt. Only filler metal is going to be melt, and that filler metal will go into the gap with the by the capillary action. The only difference in brazing and soldering is that the melting temperature of the filler metal, right? The melting temperature of the filler metal. Generally soldering will be used for neat leak proof joint. Okay, or a low resistance electrical joint, Generally you can see this type of pipe are going to be what? Thin copper pipe are going to be what? Joined with the help of what? With the help of soldering. Okay, with the help of what? With the help of soldering. Now the next is the crack. Now what type of question will be come in your GATE exam? Match the following. In the column 1 he will give this welding problem, and in column 2 he will give the causes. You have to remember this column, right? In the match the following question. Look, cracking of the weld metal. Cracking of the weld metal means there will be a crack in the joint. there will be a crack in the joint. So why the joint is going to crack? Why this joint is going to crack? Because there will be high brittleness, right? Because there will be high brittleness. Remember please, cracking of the base metal, sometime base plate. This is what? Base plate. This is what? Base plate. This is what? Base plate. Okay, this base plate is also going to be what? Crack. Why? Sometime because of excessive thermal stress. Sometime because of excessive thermal stress. Because when this joint is going to shrink, because of that shrinking, a thermal stress is going to be what? Produces. A thermal stress is going to be what? Produces, and the base plate is going to be what? Crack. Right? Spatter. Spatter, you know, liquid molten metal. Liquid molten metal will not remain in its shape. Will not remain in its shape. Suppose that this is a joint, my dear. Suppose that this is a joint. Now this joint will not give a good strength because the shape of the liquid weld pool is not good, and this is a spatter, and spatter is occur because of what? Because of the arc blow, right? Because of the arc blow, and this will not give you the good strength. Distortion. Distortion means a joint is going to be break. Why? Because you haven't selected the proper joint selection. Because you haven't select the because you selected a poor joint selection. Instead of lap joint, you have selected the T joint. Instead of corner to corner, you have to select the butt joint, right? So you have to select the joint, okay, properly. Slag inclusion. Sometime what happened, my dear? Weld pool is so large, okay, the gap between the weld pool is so large. So by single pass, it is not possible to fill the gap, okay, to fill the gap completely. So suppose that if I pass, if I'm going to pass electrode at one pass, so that much gap is going to be filled. Meanwhile, what happened? A slag will come also, right? Again the second pass, if you are not going to remove that slag, then what happened? If you are not going to remove the second pass, then there will be no proper fusion, no fusion of the liquid metal because of this slag, So you have to remove the slag when you are doing a multi-pass welding. Otherwise proper fusion will not happen. Porosity. Sometime what happen? Suppose that you have used a electrode, okay, a electrode which was placed in a very damp or moisture condition. If you use that moistured electrode, then what happen? The electrode will produce some atmospheric gases inside the arc, right, nearby the arc, and that atmospheric gases are going to trap into the weld pool, right, and that is known as a porosity. So it is highly recommended that you should bake the electrode before using the electrode, right? So thank you very much, my dear. Thank you very much.